Good morning, everyone.
Hi, Mohammed.
Hi, how are you?
I'm doing well. I think we should be, I'm setting up the YouTube link. I think we should be live now.
Mm-hmm. Yeah, I'm also preparing few things just in case. I mean, I'm setting up the master slide set and things like that just to be ready.
Yeah, that is perfect. Thank you. Yeah, I think the YouTube is working now.
Yeah, do you want to control the master slide set from your machine, or would you like me to do this for you while you speak?
Yeah, I mean, both works for me. I think if you want to handle that in terms of the presentation, you mean?
Yeah. So I think you will need also to allow us to share screen, because now host disabled participant screen sharing. This is what I did.
Okay, just give me a second.
Yeah, because I think we need to do that for all the speakers.
Yeah, I think everyone can share. So I want to also start recording. So we are live on YouTube now, and
Good morning, Mohammed and Farouk.
Good morning.
Hello there.
Hi, Farouk. Sorry, I think you have to mirror your background. It's just.
Oh yes. I just noticed that.
Yeah, that's a good observation.
Thanks, Maddie.
So, is it correct now? Yeah, I think it's good.
Not yet, for me at least.
I think it's correct, right? So I'm
not yet.
First, yeah.
Okay, what I see, it shows it's mirrored.
I think Zoom does it itself. So somewhere in the settings of Zoom, you have to say not do it or do it.
Yeah.
Okay. Is it okay now?
Yeah. Not yet. So I think what you need to go to Zoom settings, background and filters, and just say mirror my video. Yeah, or unmirror it. I think it's being set for you automatically. You just need to uncheck it.
Yeah, I just did it. I don't know what does it work now?
Yes, now it's good. Now it's
good. Okay.
Yeah, perfect. Yeah. And let me just try to see if I can share my screen.
So Mohammed, to start, I think I'll start by sharing the screen for the opening, and then I'll hand it to you, and then we go back to my talk, and then the rest of the speakers as we discussed. Okay, perfect.
Yeah, that looks great.
Hello, Suramia. Is that how you should pronounce your name?
Yeah.
Hello.
Hello. Hello, Mahdi. Hello, everyone.
Hello, and thanks for your help. Thank you.
Thank you so much for your help.
My pleasure.
Thank you so much.
Thank you.
And you got it right. It's Suramya.
Suramya, great. So we'll need help promoting people to panelists, people who are speaking. So Farouk, should it be done based on the website, or you will do it?
I'm happy either way. I think the speakers I don't see the speakers yet, so I think we will wait, and then we can promote them as panelists once they join.
Okay. I'll be here for a while if you need any help. Otherwise, I'll just turn off my camera and kind of listen.
Thank you. Thank you so much.
Thank you very much.
I think, Farouk, you would need to do this because I don't seem to have the privilege to promote any participant to panelists. So probably you would need to do that yourself.
Okay, I do it. That's not a problem. I think if
you want to do it, then you would need to be the co-host, Muhammad. So Farouk, if you can make Muhammad co-host, that will be great.
Okay, Mohammed is co-host. I'm okay, Mohammed. Yeah, and Matt is
Thank you.
And Soramia can be actually the co-host to help you with,
Okay.
bringing people out. Yeah.
Yes, that's a great idea.
So I think everyone is co-host now.
Mhm.
Sounds good.
Yeah,
Yeah.
yeah, that's great. Yeah, I'm also looking for when panelists are going to join, and then we will promote them immediately to panelists. So please, Soramya, if you notice any of the speakers, I think they will first join on the attendees list, and then we would probably then promote them to panelists, right?
Okay, because I have the list of the speakers on my other screen. The
Yeah.
moment I see, I can do that for you. No problem.
Yeah, that would be fantastic. Thank you. We really
No
appreciate
worries.
it. Thanks.
I'll do that.
So we're live on YouTube then.
Yes, we are live on YouTube. Okay.
Hi, Marcy.
Hello, Marcy. Let me.
Hello.
Oh, hi, Elena. Hi, Marcia. So it's great to see you all. So we are about to start in like 5 minutes. So Mohammed, do you see my screen? Is it shared correctly?
No, I don't see your shared screen now.
So what is it that you see?
Oh, let me just.
I see it correctly.
We can
Yeah.
see.
Yes, I can see it. Sorry, I have multiple screens and I get a little lost. Sorry for that.
That's not a problem. That's great.
Yeah, that's
okay.
the problem when you use many screens.
Yes.
Yeah,
Okay, so
yeah.
it's you are seeing the full screen or the presenter view?
Full screen, I see.
Full screen. Okay. Great. So I think the workshop is being recorded correctly, and we are also live on YouTube. And I put the YouTube link in the chat box, but I'm gonna put it again when we have more participants joining.
Everyone here can, I think, copy it from the YouTube icon on the left, I think.
That's perfect. I didn't know that. How's everything? It's great to see everyone here. I mean, with COVID, we lost contact because no conference anymore. So I think these workshops are good opportunities.
Yeah, it's really great to be here. And Farouk and Mohammed, thank you for organizing it. I'm really looking forward for all the talks.
Yeah.
Thank you for being here. Thanks for accepting our invitation. Thank you.
Yes, thank you so much. So that's great. So I think we're gonna start in 2 minutes, 2-3 minutes. So Mohammed, when I'm presenting, I cannot see the list of all participants. Is it possible for you to check and make sure if all the speakers are promoted as panelists?
Sure, we'll do that.
Thank you.
Yeah, and I think Soramaya also is looking into that as well. So
okay,
we
great.
will do this as soon as possible as we get speakers joining.
That's perfect.
Great, Etienne is here. Thanks for joining the call, and thanks for accepting our invitation. Okay.
Hi, Etienne. Okay, great. So everyone is joining.
Can you hear me?
Yes, hi, Etienne. We do hear you.
Yeah, so thank you for passing me the link, so everything is fine.
Yeah.
That's great. That's great. Thank you so much for joining us. And so we're gonna start. We can start now, I think. So in a minute, perhaps.
Yeah.
Maybe meanwhile, you can test if you can share your screen just to make sure that everything is okay.
Okay, I try.
I think the screen, Mohammed, the screen is shared already, right?
Yeah, but I mean, all the speakers can share their own screens for their own talks. Yeah.
Okay, great.
So I can try. Let me, where is it? Ah, here, yeah. Voila. Voila, can you see my screen?
Yeah.
Yes,
Looks great.
We do see your screen.
Mm-hmm.
Yeah, so you see yourself, right? Yeah.
Yeah.
Okay, so somebody else can try.
Marcy, would you like to just try if your share screen is working perfectly?
What do you want, sorry?
Yeah, looks great.
Perfect.
Okay. Yeah, Marcia is here. Yeah. Great.
Eliana?
I can try it now.
Yeah.
See the presentation?
Yes, we do see it.
Yes.
Okay, I think we can start. So let me share the screen again and so do you see my screen? Yep. And it's full screen, right? It's not the presenter view. Okay, great, perfect. So let's start. So I think we are we are on YouTube and everything is being recorded. So hello everyone. Thank you so much for joining us today at our workshop, which is NeuroHaptics, Touch with the Brain, as part of Fourth Haptics Conference 2021. My name is Atashzar, Assistant Professor at New York University. In collaboration with the workshop co-organizer and my colleague, Mohammed Aid, Assistant Professor, New York University, Abu Dhabi, we would like to welcome you to NeuroHaptics workshop. Before we get started, I would like to go over a couple of housekeeping items. So the workshop is being recorded and broadcasted on YouTube. So you can see the link to the workshop here, and also we will post it in the chat box. So full workshop information, including a speaker's name and details about the talks, can be found on the workshop webpage. And actually, the link to the excuse me, and actually the YouTube link is also on the webpage of the workshop, and also we will post all the links on the chat box of this event. So we encourage interactive communication, and so at any time, if you have any question, please feel free to type in your question, and we will go over the question and pose it to our speakers at the end of their talks. So on behalf of the workshop organizers, I would like to sincerely thank the invited speakers, which made it possible for us to organize this unique event. Thank you so much. It's very much appreciated. So the workshop is composed of 8 talks, in addition to a roundtable discussion, during which we are going to ask all the panelists to share their opinions about some of the open topics and questions in the field. So here is the mission statement for our workshop. So in this workshop, we collect expert opinions from researchers who have been actively contributing to the field of haptics and neuroscience. This workshop seeks to present and discuss recent efforts related to neuroscientific models of human sense of touch and combination of that with advanced neurorehabilitation robotic technologies. So the goal of the goal of this workshop is to bring together diverse researchers from both haptics and neuroscience fields and background, and explore how to maximize the progress in this multidisciplinary field, in addition to inform and further accelerate research in both the haptics and neuroscience communities. We sincerely hope that these workshops create an interdisciplinary and interactive dialogue between leading researchers, young researchers, and the clinical industrial sectors, focusing on neurohaptics, bringing new perspectives in the synergy between haptics and neuroscience. So with that introduction, I would like to ask the co-organizer, Mohammed, to take it from here.
Thank you very much, Farouk, for the introduction. I'd like to welcome everybody, the audience, also to the call. And I would just give a brief overview of the program. So we will start with we will have a total of 8 talks. Each one will be 20 minutes. We will have also 5 minutes of Q&A. And after each 2 talks, we will have about 10 minutes of a break. And at the end of the workshop, we will have an open panel discussion for questions about challenges, maybe future perspectives in this field. So with no further ado, I think we can start with the first presentation, and that will be given by Farouk Atashzar, and he's an assistant professor at New York University, Tandon School of Engineering, and his talk will be haptic modulation and motor control. So Farouk, the floor is yours. Go ahead.
Thank you so much, Mohammed, for the introduction. I would like to say that the reason that we put my talk at the beginning was so that after that, I can manage I can help with managing the workshop and handling the questions and background. So again, hello everyone. So at New York University, I lead the lab called Medical Robotics and Intelligent Interactive Technologies Merit Lab. And I'm part of both Department of Electrical and Computer Engineering, Mechanical and Aerospace Engineering, and I'm also affiliated with NYU CUSP and NYU Wireless. So the lab was founded in August 2019, just before the pandemic, and we are very excited about all the industrial, clinical, and academic collaboration we have, helping us to connect human neurophysiology with machine intelligence. Because we're interested in closing the loop of interaction between human and machines using AI, biosignal processing, wearable technologies, and robotics. And in terms of haptics, we focus on the intersection of we focus on the interaction between haptics for machines and haptics for human. So we call the first one, which is haptics for human, as feedback path, and the second one, which is haptics for machine, as the feed-forward path. So like I said, the lab was founded in August 2019, just before the pandemic, and when pandemic happens, New York was the epicenter of the condition. So we were very lucky and pleased to receive NSF funding, making it possible for us to convert and channelize some of the research that we have done in the area of haptics to the fight against the pandemic. And we did that using the concept of wearable technologies. So how we did that? So when we talk about haptics for machine, we mean when machine can perceive human neurophysiology using the vibration generated by human body. And COVID-19 infection is an infection for respiratory disease, meaning that by listening to the sound of breathing and by measuring the vibration caused by breathing, we can actually extract a lot of useful information in the context of wearable technology, and we can convert that to IoT wearable technology and then decode that to understand the symptoms of COVID-19 and then generate connected to cloud to track the distribution of the disease in a society. So we propose the concept of system for symptom decoding and systems for spread tracing, and the results can be found here. So, but this work was actually rooted in one of the recent research that we have conducted, again, under the umbrella of haptics for machine, when we actually use the modality which is called mechanomyography, and we specifically generate a new modality, we call it MMG+1, which allows us to listen to the sound and vibration generated by motor unit recruitment in the muscle to decode and track the intention of human motor intention. So like I said here, you can see the result of the paper we published in artery transactional neurosystem rehabilitation engineering. And you can see the wearable system that allows us to actually get access into the very deep vibrations of the muscle. So then, of course, we conducted a lot of AI research using deep learning models and explainable deep learning models to be able to not only decode the motor intention of the user, but also to understand which part of that vibration the machine is paying attention to. So this was a first theme I wanted to mention, which is haptics for machine. Now I want to go to the feedback path, which is more conventional way of thinking about haptics, and that's haptics for human. And in this regard, I want to touch different projects to discuss different types and themes of haptics. So the first one I would like to talk about is haptics for neurorehabilitation. In this regard, we are very much interested in the concept of telemedicine because we want to bring robots to the homes of patients. And we believe that's possible under the topic of tactile internet, which wasn't before possible because of the very intensive quality of service requirement for this technology, which is ultra low latency of 1 millisecond round trip and ultra high reliability of 10 to the power of -9. And now, thanks to the technology of 5G and 6G and beyond, we believe it is possible to go to the direction of tactile internet and combine that with haptics and robotics to bring robotic system to the homes of patients and to bring the point of care and point of therapy and rehabilitation to the homes of patients. So this topic has attracted a lot of interest from different industries. For example, here you can see a snapshot of Ericsson talking about 5G and tactile internet, which will be the future generation of mobile internet. So using this concept, and like I mentioned, we are interested to bring the point of therapy to the homes of patients. And for doing that, we first need to make a robotic system that can be placed in patients' home. So this is the robotic system that we designed, and we released the design of it in 2020 in IEEE Transactions on Medical Robotics, a foldable robotic system, which can be used for both upper limb and lower limb, 5 degrees of freedom, a very compact sized robotic system, which you can place in a backpack and connect it to the machine using a cable. So now we have a robotic system which can be placed in patients' home. The next step will be to connect that to the therapist, which can be in clinic. Then if we can do that using a telerobotic concept, then we can connect a clinic, an in-clinic therapist to an in-home patient and deliver kinesthetic interaction between therapists and patients. And we call that telerobotic rehabilitation, which is under the umbrella of telemedicine. And it's very interesting for us because it allows us to have a remote access for and remote therapy. So of course, but when we talk about rehabilitation, we are talking about higher forces and often high frequency forces because of the involuntary motions of the patient. And over internet, there is a concern of instability. To address that, we specifically investigated a particular feature of human biomechanics. We call it excess of passivity. So excess of passivity of human biomechanics allows us to understand the capability of human biomechanics in absorbing the mechanical energy. And then we use that. If we can use that in the design of intelligent controllers, we can unleash the power of robotic system and allows to maximize and it allows us to maximize the transparency and the performance of robotic rehabilitation systems. And we did that for both upper limb and for also lower limb. And this work was collaboration with Etienne, who is one of the speakers today also. So we believe the future, one of the futures of robotic rehabilitation will be telerobotic rehabilitation. Like I said, when we can have human and patients and therapists connected over internet, and we can deliver kinesthetic rehabilitation remotely and over internet. And we are very much interested in this topic because what happened during pandemics, when many patients who experienced a stroke, there was concerns for those patients to go to hospitals and get rehabilitation because the same patients are also in the same range of age that can be affected by the pandemic the most. So our concepts in this regard was published in a perspective review paper that we published in Frontiers in Robotics and AI. And in this work, we actually discuss different modalities of robotic system, including telerobotic system, exoskeletons, and wearable robotic system, and how those modalities of robotic system interact with different modalities of healthcare, including rehabilitation, assistance, and assessment, and how we can talk and think about combining these two spectrums and thinking about the future and how we can help the future. So I want to switch gear now and talk about the different type of haptic system. And now I'm going to talk about haptics for assistance. In this work, I would like to present some of the results that we have conducted for a condition called writer's cramp or task-specific focal hand dystonia, which is the condition caused by damage in the basal ganglia of the brain, which affects patients to conduct very fine motor tasks. So patients with focal hand dystonia, they don't have any problem doing coarse motion or large motion. But when it comes to fine motor tasks, they get into this painful and abnormal postures, involuntary, and then it causes the pain and sometimes the tremor. And it's a condition which can affect their fine motor task. For example, on the bottom, you can see a drawing of a patient having the same condition. So in the literature, to help those patients, there is this historical devices, mechanical devices that those patients can use to write, for example, here in this case. But if you think about that, by doing that, you are not changing the motor output. What we're changing is the sense of touch. And that's exactly what we wanted to investigate. So before talking about what we've done, I want to quickly talk about the current therapy. So the current therapy in clinic is to use botulinum toxin injection therapy, basically Botox, that a neurologist inject to relax the muscle, which is more responsible for that. So in our work, we wanted to examine haptic manipulation or haptic modulation compared to botulinum toxin injection. So in this work, we have this fully sensorized setup. We had a 60 degree of freedom force sensor in a table. The whole pen was sensorized. We had the electromagnetic tracker at the tip of the pen measuring 60 degree of freedoms of motion. And also we measured the grip pressure, and full upper body of the patient was also sensorized to objectively track the performance of the patient. And why we had the robot here? And we had the robot to generate a viscoelastic, a tunable viscoelastic virtual writing surface for the patient, so the patient can generate the same writing task, but then we change the haptic response using the robotic system. The result was very much interesting. So it was very interesting. By haptic manipulation, we are able to improve the performance of those patients by 57%. And when you compare that with injection only, which you can see on the top right, it allows us, injection only allows us to get into 39%. And when you combine that, we go up to 64%. And that shows, and this is the first result, showing that haptic manipulation can significantly help patients with writer's cramp. So if you look into different participant results, you can see that, interestingly, for some participants, the benefit is additive. Like the participant 1, the blue color shows the performance of the patient over the 5 sessions of assessment and therapy. So at the end of session 1 and session 3, we inject patient with Botox. But then for participant number 4, you can see the benefit of the robotic system, which is the blue color, is nonlinear. After the second session using robotic system, the patients got almost perfectly improved, but still when you just check the effect of injection, you don't get to that point. So that shows that this benefit of haptic manipulation is not a linear phenomenon. So again, let's switch gear and talk about the different type of haptics. Again, still thinking about assistance. And here I want to talk about spatial haptics for proprioception. And this is important for people with a lack of a biological limb. So in this work, we generate a wearable system with 8 vibratactile motors around the arm of the patient. And then we investigate the different patterns of haptic vibration feedback. So you can see 4 different patterns that we investigated. So we wanted to understand if using this spatial distribution of vibration around the limb of the patient can actually regenerate the proprioception. The user can regenerate the lost proprioception. So we conducted this study on healthy subjects, but in order to block their natural perception and visual feedback, we asked them to do a task in virtual reality environment, but then we apply a nonlinear mapping between the hand motion and visual feedback. So to completely perturb the natural hand-eye coordination so that they rely more on the haptic feedback. So here you can see the result on the bottom line here. On the left, when the haptic system is turned off, you can see the participant is not able to reach the target, and basically the participant is exploring the whole workspace to get to the target. But when we turn on this spatial distribution of haptic feedback, the participant is able to track, to navigate in that nonlinear skewed visual field and get to the target very nicely. And that's basically due to this spatial distribution of haptic feedback. And the result of this work was published in Journal of Neural Engineering in 2020. So as the last part and the continuation of the same work, we also think about how we can modulate the frequency. So in this work, we generated a new wearable technology in which we had a vibratactile motor connected to a solenoid. So we had a high frequency haptic and we have a low frequency haptic also. And by combination of the two, we wanted to see if we can provide and regenerate this time the stiffness perception instead of proprioception in the previous work. So in this work, we focus on closed loop haptic, meaning that we measure the electromyography of the patient's limb, and then using that, we predict their motor input, and then we provide the vibratactile feedback. So there's a lot of details in the result. I just want to mention that we use psychometric graphs and psychometric studies, including point of subjective equality and Weber's fraction. And for four objects, a large and a small object with low and high stiffness. So the very important point that I want you to pay attention is Weber's fraction. And we observed that we are able to get to the Weber's fraction of 0.09 or 0.11, which is very important. The lower this value, the higher the precision of the perception. And to compare that, human natural perception of a stiffness has the Weber's fraction of 0.08. And that shows that we are very close to natural perception of a stiffness using the modulation of the two frequencies and wearable technology. So I would like to end my talk by saying that, again, the focus of our lab is on closed loop haptics when we combine the human sense of touch with machine sense of touch to close the loop of interaction between human and machine. I would like to thank all the colleagues, and of course the projects that I presented was not only me. There was a team of great collaborators, sources of fundings which make it possible for us to conduct the task, and a lot of great students who did the work actually. So, and thank you all for attending my talk and this workshop. And if you have any question, I'll be more than happy to answer. Mohammed.
All right, thank you very much, Farouk, for the great talk. And I think now we can take a few questions. I think we have time for a few questions. I'm looking up in the chat box if there are any. Let me see.
Can I ask meanwhile?
Yes, please, go ahead.
Hi, so Farouk, thank you for a very nice talk. And I actually have a question about the writer's cramp treatment, because it seems, based on what you presented, that actually the Botox injection could make the situation worse for them. And the haptic modulation was, I guess, it seemed like what you're proposing is much more effective than the standard treatment. So can you elaborate on it a little bit more?
Yeah, sure. Yeah, thank you. Thank you so much. That's a great point that you mentioned, actually. As you mentioned perfectly, for one of the subjects, for some of the subjects, the performance was actually negative. So, and that's correct. One of the problems with Botox injection is that it results in the weakness. I mean, patients, if the injection is not accurately tuned, it may result in a little bit of a weakness of the motor task, and that can affect the performance also. And that's one of the challenges for Botox injection, because you never know how much is enough, and there's a lot of course, the neurologist should have a lot of practice and tuning, but for many patients, the response is nonlinear. So that may affect it. So that's actually why we wanted to investigate other possibilities. And we're very interested to see that with the haptic only, we always had positive improvement, and the improvement was, the average of improvement was 60%. But when we had Botox injection, as you mentioned, for some of the subjects, the performance actually dropped because of the weakness in their muscles. That actually was the reason for that negative. But that's a great observation. I don't know if it makes sense, the answer.
Yeah, thank you. It really makes sense. It sounds like they should go with your solution rather than continue with the Botox.
Thank you so much. Yeah, I mean, this is interesting that haptics play an important role. Like I said before, when we started this work, there was a lot of question about if it's the motor output problem only, or sensory input has some important role. So for cervical dystonia, we know sensory input can play a lot of role. For focal hand dystonia, we did not know that. But then after this study, we showed that haptics can play a big important role in that. So yeah, I mean, I'm very excited to continue this work, and hopefully we get into some new results.
I don't want to hijack the questions, but if there are no other questions, I'd like to follow up on this.
Yeah, I had a question, but please go ahead.
I just wonder if you tried, because you here applied actually force, did you try to take that apart into seeing whether it's actually the support, the actual force that is being applied, or maybe even some wearable solution can be sufficient if it's a matter of stimulation of the haptic sense and the sensing?
Yeah, that's a great question, actually. Thank you. So we investigated different postures. We investigated actually blocking their vision to see what if the vision is playing a role. The vision didn't change it much. The posture in different postures didn't change it much. But the wearable, if you provide the wearable or tactile kind of feedback, that's a great question. We didn't test it for this population, and I'm excited. Actually, it's a great question that we didn't think about that, and that can be actually, I think, done, and we can see if that can help them We tried to actually focus on vision and haptics, but vision wasn't responding much. But haptics, by kinesthetic kind of feedback, it was changing their performance. Vibratactile can be also a great investigation, actually. And thanks for asking. We didn't do that, but I think that can be a future direction.
Yeah.
Thank you.
So maybe I can also ask a question regarding the array of vibrotactile actuators that you've used around the arm. And I just wanted to ask if, I think there has been a question, so I'll take it later. But so I wonder if you have tested with different kind of actuation patterns, like providing maybe apparent motion around the arm, maybe to provide directional cues or things like that. Have you thought or have you experimented with this?
Yeah, this is a great question also. Thank you. So, I mean, yes, as you can see here, we investigated 4 types of patterns of vibration, and the direction changes. So that's why we call it spatial haptics, because the directionality changes based on the direction of action. So we predict the direction, the intention, and then using that intention based on the electromyography, actually, we change the directionality. So the vibration, the field of vibration changes around the arm of the patient. And so we modulate the intensity and the direction. But the way that we modulate the intensity, there was a question how we want to, are we going to only use one motor, like the one that you see on the bottom, or are you going to use multiple motors, and how we are going to change the intensity? So we were investigating different patterns, and we found one of the patterns performing the best. But yes, the field of vibration was rotating around the limb, and that was how actually subjects was able to navigate in the space. So that's based on the directionality of that haptic field, and they're able to rely on that and navigate in this nonlinear visual field. But without that, you can see here, they are not able to, they just explore the whole space. So the directionality was an important factor, as you mentioned, yeah.
So these vibration motors are all actuated at the same time, or they are actuated in time sequence, or?
So it depends on the direction. For example, if you are around here, this one is only active. So based on the direction that the patient is trying to move, the subject is trying to move, we change the directionality. So again, different patterns have different types. So for example, this one, we only use one motor, and then you increase the intensity, we go to 2 motors, you increase the intensity, we go to 3 and 4. But here, we don't increase the number of motors, we just increase the vibration intensity of that one motor. And then the direction depends on the direction of the rotation, and continuously we change that. It's like a wave. I mean, when you wear it, it's like a wave going around the limb.
Yeah, thank you very much. And I think there is a related question in the chat box here about from Rania Hassan about the spatial distribution of these motors.
So could you elaborate on the spatial distribution on the motors? So that's a great question. We actually try to have a standard distribution based on some biomarkers of the patient, of the subjects, to make sure for all the subjects we put the motors in a same location based on where the muscles are. But that's something that can be investigated. Because we had 8 motors, there was not much of a space to investigate. But what we try to control for that and try to have the same distribution for same subjects. Yeah. I don't know if that answered the question. Yeah.
Yeah, there's one last question, I think, in the Q&A, and this is from Alex. And the question is, I can read this for you. How do you think haptic feedback would assist other forms of dystonia, like Parkinson's disease?
So thanks for the question. Parkinson may not, I mean, I'm not a neurologist, but I think Parkinson cannot be categorized as a dystonia. So dystonia and Parkinson are 2 different types of neurological disease. For dystonia, we have cervical dystonia, which is on the neck, or focal hand dystonia, which is on the hand. For the cervical dystonia, there was a lot of research that sensory input can help with cervical dystonia, and actually haptic can help. And there's I think 5-6 groups that I know they're working on that. For focal hand dystonia, we were not aware of any other groups working on it, so we started this work. For Parkinson's, I think there is a lot of work in haptics for Parkinson's. I haven't done research in haptics for Parkinson's. We have done work in Parkinson's only, but not haptics for Parkinson's patients. But I have seen a couple of interesting research on providing vibrotactile feedback, and if it can help with tremor for Parkinson's patients. And if you want, I can send you the paper. I think Dario team in Imperial College. He did some work before I joined Imperial at the time. Yeah.
Thank you very much, Farouk, for this great discussion. And
thank you, and everyone
for the great questions. I think for the sake of the time, we should move on to the next talk. And I'm delighted to introduce Professor Marcia O'Malley. She's a professor of mechanical engineering and computer science at Rice University, and her talk will be entitled Human Perception of Wearable Haptic Cues. So the floor is yours. Thank you very much for joining us.
Thank you. Let me get myself set up here. You see my slides all right?
Yes, perfectly.
Great. All right, well, thank you so much, Farouk and Mohammed, for organizing this workshop. I'm really excited to discuss my own perspectives on neurohaptics and how we might come to understand, more complex neural representation that we can record from the brain in response to touch stimuli. So the talk today is really recent work by my PhD student, Alex Macklin, who asked that question of you earlier. So happy to share what she's been up to. So for the past few years, my lab's been interested in how we can communicate complex information to users via wearable haptic devices. So there's a range of applications where this might be useful. We could receive messages from our in-home robotic vacuums telling us that it's time to change to charge, or get intuitive instructions when navigating highways, or even enhance our Zoom calls with haptic exchanges. So to successfully communicate via a wearable haptic device, individuals must not only reliably perceive the cues themselves, but they also must learn the mappings between these complex cues and the information they encode. So here I show our missive wearable haptic device that I'll talk more about later in my slides. This device is used to encode phonemes, which are defined as any of the perceptually distinct units of sound that distinguish one word from another. So here the cue stretch off, squeeze on, top tactor, long vibration must be perceived accurately, and then translated to its phonemic counterpart, hear the sound aw, as in the word awful. So our missive device conveys cues that are comprised of squeeze, skin stretch, and different vibration stimuli that can be presented at one of 4 different vibrotactile locations. My group has designed several different wearable haptic devices, and most of these devices convey what we call multisensory cues, which we define as cues that are comprised of several simultaneously displayed cutaneous haptic sensations. So in the case of missive, that would be the simultaneous display of stretch, squeeze, and/or vibration cues. We've extensively studied the perception of these multisensory cues, and details of this work can be found in 2 papers that were published recently in the Transactions on Haptics. So in this video, you can see a user identifying the haptic cue itself. So identifying the various components of this multisensory haptic cue that's conveyed to the arm through our missive device. And again, these are combinations of skin stretch, radial squeeze, and several different vibration cues. We've also studied the ability of participants to learn to map these multisensory cues to phonemes, and then string those phonemes together into words. And that's primarily the work of Nathan Dunkelberger that is that recent TOH paper. So this video shows a user playing phonemic haptic cues in sequence. Make sure that it's going to play. There we go. So this video shows a user playing these phonemic haptic cues in sequence and then identifying the word that is comprised of those distinct haptic tokens. So each phoneme in a word has its own multisensory haptic cue. They feel those one at a time. And then once they've received all the phonemes for a word, then they're asked to select which word. And we've also done free response type investigations. So we were interested, and mostly Alex was interested and convinced me that this was a really cool problem to see if we could determine if we could use neural measures of learning in addition to the behavioral measures that we had previously investigated to gain insight into how users learn to associate multisensory haptic cues with their phonemic counterparts. So for this study that I'm going to describe, we selected 39 multisensory haptic cues for which cue identification performance was verified to be quite good. And we mapped those 39 multisensory haptic cues to 39 phonemes. So this figure represents that full mapping. The 4 quadrants of each subfigure represent vibrotactile location, and the top, middle, and bottom squares in each quadrant represent short, long, and double vibrotactile cues. Cues represented with orange blocks are when stretch is on, while white is when stretch is off, and all the cues in the green panel correspond to squeeze being activated. So for example, ah as in awful is mapped to a cue that's comprised of squeeze on, skin stretch off, and the right vibrotactile active with a long vibration cue. As in it is mapped to a cue that's comprised of squeeze on, skin stretch on, and the top vibrotactile active with a double vibration cue. And one more example, ch as in chew is mapped to a cue that's comprised of squeeze off, skin stretch on, and the right vibrotactile active with a long vibration cue. So we would like to better understand the changes that take place at the neural level, specifically after training on haptic devices. So we were curious how training and exposure on missive and getting used to these multisensory haptic cues might be represented in the brain. So non-invasive neural recording techniques are one way that we can investigate this. And EEG, or electroencephalography in particular, allows us to measure the electrical activity of the brain via many electrodes placed on the scalp. This technique allows us to capture activity of the brain across many channels, and we can use this approach to capture the brain's response to these haptic cues. So it's well known that changes due to training or learning can be reflected in changes in neural activity. In this way, exposure to haptic cues may evoke neural activity in one way prior to training, but then after training, the neural activity may start to look different. For example, we might see differences in the amplitude of response or the timing when a certain cue is presented. We were particularly interested if, after training, individuals would be better able to distinguish between the haptic cues presented on missive, and if this would be represented in neural activity captured by EEG. So we used representational similarity analysis, or RSA, as the framework to address this question. So I'm going to present the RSA framework with a simple example, and then I'll explain Alex's analysis and results, where we characterize, how the neural response to the haptic cues changes with training. So representational similarity analysis, or what I'll refer to now as RSA, allows us to evaluate how similar stimuli in a unique set are represented neurally. So first, we record neural activity as an individual receives the unique haptic stimuli. In the scenario here, 2 of the cues are more similar with respect to the haptic features that are being actuated, where the top and middle cues differ only in terms of where vibration is actuated. Everything else is the same. And the final cue is different with respect to multiple features. It involves stretch instead of squeeze. So it's much more perceptually different. The top 2 haptic cues being more similar to each other with respect to these haptic features that are actuated would naturally lead us to expect that the neural representation of those, when those 2 cues are conveyed to the user, would be more similar than the neural response to the 3rd cue. So RSA gives us a way to quantify these similarities and differences. It allows us to quantify how similar the neural activity pattern is across all the channels recorded at each time point considered. So to break this down a little bit more, if we imagine that we are considering the neural response patterns to each cue at time point t, we can represent these neural activity patterns captured across the channels in vectors of voltage values, or the unit of signal recorded. We can then determine how similar these neural patterns are by correlating each of these vectors for all pairs of stimuli, where patterns that are similar will have a correlation value close to 1, and those that are dissimilar will have a correlation closer to 0. We can then populate a representational similarity matrix to have a 2D representational space of how the brain represents a unique set of stimuli. So here we take those correlation values and just populate this 3x3 matrix, where we can see that the comparisons between cues that are similar here, the Q1 compared to Q2 are going to have a high correlation. And when we compare the cues that are more dissimilar, that is comparing 1 to 3 or 2 to 3, we're going to see those correlation values much smaller. And then we can, in this way, we reduce this high dimensional neural representation of unique stimuli into a visual 2D space, which we call the brain-based similarity matrix. That represents how similar the brain response to a particular stimulus is to every other stimulus considered. And you can create these, again, at every instant in time for which you've recorded data. What's unique about RSA is that we can compare the brain-based similarity matrices to model-based ones to test hypotheses on how we think the neural representational space to a set of stimuli may be structured. So the model provides a theoretical or conceptual structure of how similar the stimuli being evaluated actually are to each other, which hypothetically then the brain may reflect. So the brain-based similarity matrix is DAL data coming from the EEG, and this model similarity matrix is something that we need to construct. So one logical model for how the neural representation to missive cues may be structured is one that represents how similar or dissimilar each missive cue is to every other cue with respect to the features that make up each cue. So again, remember our missive device has stretch, squeeze, and vibration, and those vibration cues can vary and at different locations. And so you can imagine that for our cues 1 and 2 that are similar except for vibrotactor location, those would only differ by one feature. For here the example being vibration location, whereas 1 and 3 would differ by 3 or 4 different types of cues. So one has stretch, the other has squeeze, the vibration is happening in a different location and it's a different vibration cue. So we can generate this, this feature space or this model by counting the number of features that are different between each cue, where that could be location or type of vibrational cue, whether squeeze was on or off, or a stretch cue was present. And in this way, we represent cues that have 0 different features with the value 0. That means they have high similarity. In this case, they're identical, all the way to -4, right here, meaning that the cues are very, very different. So this model then can also be translated to a visual representation, and it's representative of how each cue is related to every other cue based on the cue features themselves. We could then compare the brain-based response to that of the theoretical missive feature space, and if the two are similar, then we could deduce that the individual processes the haptic cues in a way that is sensitive to these slight differences between the physically rendered cues themselves. So we used this approach to determine if brain-based similarity of multi-sensory haptic cues presented with missive started to reflect the feature space of the cues themselves after training on the missive device. We conducted an exploratory study to evaluate the potential for this representational similarity analysis, or RSA, as a quantitative tool for tracking neural changes of haptic learning. We had 2 questions. First, does learning on a multi-sensory haptic device make an individual more sensitive to the differences in between the haptic cues? And how does the sensory space to haptic cues change with directed practice? We had access to a preliminary data set where EEG was recorded during passive exposure to 9 unique missive cues, which were each made up of a unique haptic features. That's vibration location, stretch, or squeeze. The cues all varied by at least one feature, and the cues are modeled here with these little icons. EEG sessions were recorded both before and after 4 days of active training with the missive device. Using these EEG recordings, we then determined the brain-based similarity of each haptic cue to every other haptic cue, both before and after training. The same methodology that I laid out before was implemented here, and brain-based similarity matrices were computed for each time point considered. Then we determined a missive feature space similarity matrix, this time with respect to all 9 missive cues. The model feature space represents, again, how similar each missive cue was to every other cue based on the similarity of the haptic features that were actuated in each cue. So again, the main diagonal of this matrix is going to be most similar because that's where we compare each Q to itself. And then the darker the blocks, the more similar that Q is to another Q, and the lighter the block, the less similar the block is to, or that Q is to another Q. So we hypothesized that the brain-based representation that we would extract from EEG would reflect this model after training, as individuals should become more sensitive to the differences between each multisensory cue after training. So we tested how similar the neural space was to the missive feature space at every single time point, both before and after training, by correlating the representational similarity spaces at each point. So for each point in time of the recording pre-training, we compared the RSA, the brain-based similarity matrix on the left, to our model feature space on the right. And then we did this after training. So in these comparisons, the model is always the same, and we're comparing pre-training to post-training correlations. So here we plot the correlation value determined at each time point. So time on the x-axis, correlation on the y-axis for the brain-based similarity matrix compared to the missive feature space. We considered analysis with respect to the end of the longest possible vibration feature. We found that after training, the neural response to missive cues was more similar to the theoretical feature space after training, right? So again, here, blue is post-training, orange is pre-training, and you can see these correlation values slightly higher here. The black bar at the top is the region where the correlation is significantly greater than 0. So this was preliminary work, so take that as a caveat, but we're excited about the potential for RSA to serve as a quantitative method to track neural changes associated with learning on a haptic device. So to just summarize what we've done, we used RSA to evaluate if practice on missive made the individual more sensitive to any differences between the cues that they were experiencing. Our results suggest that practice with missive leads to a sharpening of the sensory response to multisensory haptic cues. And this pilot study demonstrates the feasibility of RSA as a quantitative indicator to track neural changes associated with training. Going forward, we plan to collect data from additional participants. Further, we're interested in exploring other feature space models that integrate our knowledge of how people perceive these multisensory cues. So for example, instead of attributing each cue component a value of 1, giving integer-based similarity scores, we could use our detailed analysis of multisensory cue perception that indicated that stretch and squeeze cues may be perceived as more similar than a squeeze cue in one of our vibration cues. So we could come up with a more complex model that may shed more light on how this representation neurally changes with training. We also plan to extend this analysis to haptic language perception and further explore the effects of training. So thanks for your attention today.
Thank you very much for the great, inspiring talk. That was really great. Thank you. I think we have time for questions from the audience. Let me see if there are any questions. Well, maybe I can start by asking. Yeah, please go ahead, Katerina, please.
Sorry, thank you. Thank you. This amazing talk, very inspiring indeed, this correlation between things. I just wondered at the very beginning, what made you choose these particular modalities and their corresponding experiences?
So there was a number of motivations, not always our own choosing. So this work on haptic language let me see if I can get myself to a better slide. So this work on haptic transmission of language was really motivated by some sponsored research by Facebook Reality Labs. And they had a number of different projects that were exploring lots of different ways that we can communicate haptically. So some of that work was affective haptics, how we convey emotion through haptics, and some of that was specifically language. And our focus, our directive I dare say our directive was to explore mapping based on phonemes. So we were constrained in that early work to phonemes. And then secondly, because we had done some other previous work in what we call multisensory haptics for applications like in prosthetics, we were interested in how we could map grasping of objects. So map a kinesthetic cue to grasp force and map a slip of an object to a vibration cue. We found that this was really quite advantageous over trying to use single sensory haptic devices. So using a single modality of vibration only or squeeze only. So we thought that this was a natural way of looking at encoding language by using these cues that are comprised of multiple types of cutaneous effects. We were also constrained by footprint. So while some folks, and I know Han and Charlotte are on this this webinar, their approach has been to use vibration arrays where they can create almost what I would call, or they would call gestures, right? Haptic gestures that correspond to phonemes. There you have the advantage of real estate, which we were also asked to try to keep this to something more like an armband or a wearable.
Yeah, thank you. There is also a question in the chat box. I'm going to read it for you. Sorry if I've missed this. This is from Ravali, but can you let us know what is the training period for the participants?
Sure. So I mentioned briefly a couple of different experiments. So just with the slide that I have up here, the training to learn the haptic cues, map to phonemes, map to words, that was 4 days, a total of 100 minutes of training to do multiple choice recognition of words. And then an additional several days adding, I think, another 60 minutes to do free response of words. And that's detailed in the paper by Dunkelberger et al. For the RSA work I presented today, the exposure was, I should ask Alex to help me out on this. It was 4 days of training, and the exposure on each day would have been experiencing those multisensory haptic cues for approximately, well, less than an hour a day. I'm certain it was less than an hour. Yeah, so she's helping me out in the chat. Always good to have the PhD student on the call when you're giving the talk. Thank you, Alex.
Thank you very much. I think we can have another question that's coming from the chat box, also from Jonathan, which is, by the way, very similar to my question. I'm glad that Jonathan, you asked this. So I imagine the neural representation is highly dependent on the number of EEG channels measured, as well as their spatial location. So did you use channels that are neurologically associated with the stimuli, for example, in the somatosensory cortex, or did you look into specific areas of the brain?
So my recollection of this one subject pilot is that we did not specialize or hone in on any particular electrodes. I can follow up with Alex and get back to you, Jonathan, with some more details on how we selected that. But this was purely like, this was exploratory work to just see if there might be something here to support our pursuit of this as a way of quantifying haptic learning. And so, yeah.
Thank you. We also have another question from Ilana. And the question is, I'm curious about the design process of the phonemes.
Right, I'll explain the question. I guess that probably there was some kind of logic of how you make an like what is the process? I'm curious about the process and the thinking.
Yeah, this
probably
is a great question.
Talk on that.
This is a great question. So initially, our plan was, inspired by Han and Tan and Charlotte Reed's approach, was to do something what I would call intuitive, right? Like, so what should an ooh feel like? But we were really motivated to explore an alternative approach. So we initially did basically like cue identification experiments. So purely psychophysical experiments where if I give you this component, the multi-component cue, how accurately can you identify the components? From that, we learned, and it's visible here in this slide, that there's a lot of mistakes made, especially when stretch and squeeze are both present. So if we always have a vibration cue. We sometimes have a stretch cue and we sometimes have a squeeze cue. So the red ones are squeeze only, the blue, well, squeeze and vibration. The blue ones are stretch and vibration, and the purple ones are stretch, squeeze, and vibration. When all three were present, people missed the stretch cue. And so that motivated us to sort of minimize how many cues we used that had all three, vibration, stretch, and squeeze. we then, we did a little bit of intuition. So vowels tend to be longer phonemes. So those include squeeze, where consonants do not include squeeze. But beyond that, we actually used more of an optimization-based approach. So we assigned phonemes to cues to minimize cue confusion that would also affect phoneme confusion. So if you have two phonemes that sound similar, they would be mapped to haptic cues that are actually quite different. So that if you mixed up the phoneme perception or the cue perception, you wouldn't, you might be able to then infer the appropriate phoneme. So yeah. Some details are on that in the Dunkelberger paper about how we did that.
Fascinating. Like,
yeah, it was interesting because I wanted it to be intuitive. I wanted there to be like, oh, of course, if we make them all intuitive, they'll be easier to learn. But it actually wasn't the case. So we tried several different mappings and showed that performance could reach the same level independent of the mapping that we used. And so we adopted a mapping that tries to minimize this cue and phoneme confusion.
Excellent, thank you. I think there are a few more questions in the chat box. If you don't mind, I can read one from Juan asking, expanding on RSA for the purposes of the massive device, would the RSA technique be able to evaluate the effectiveness of massive to communicate language? And his second question is, he's curious about the use of the device and whether it would introduce any electromagnetic noise into the EEG electrodes. Thank you.
Sure, great question. So this is exactly what we're interested in. So this work is part of a really interesting multidisciplinary collaboration that we're just building. So myself working on the haptics and touch perception side, working with Jeff Yao at Baylor College of Medicine, who's an expert in neuroscience and perception of touch. He does a lot of EEG and fMRI on touch perception. And then Simon Fisher-Baum here at Rice, who uses EEG and RSA analysis techniques. He studies language cognition, specifically in stroke impaired individuals. So we've got a language person who's interested in sort of that representation in the brain, how that changes with injury. Here we're interested in exactly what you described. Can we see haptic language representation in the brain, approaching that maybe with expertise to what we would see with oral or visual communication of language? On the second part of the question, I don't think we had any issues with electromagnetic noise with the EEG electrodes. There was some distance away from the device to the EEG, and I don't believe we needed to do any special insulation.
Yeah, thank you very much. There are a couple of more questions. So maybe one of them is related about did you see any effects or do you expect any effects of age groups?
So we haven't done any age-related work in my group. I do think that there will be, but I suspect age-related differences might have more to do with the haptic perception and how maybe perceptual sensitivity may decline with age. I don't know that we would see, I think generally we would see the same trend, that there would be with training, with further exposure to the cues, that we would see better representation mapped to the, between the model space and the brain-based space.
Excellent, thank you. And maybe the last question is from Rania, and she's asking about whether you see any effect for the length of the word.
Yes, so we, the video showed just 2 words there that were relatively small. I think in our word set, our average number of phonemes per word was closer to 3 or 4. And so we tested words that had anywhere from 2 to 5 phonemes. And we didn't really see an effect of that word length on accurate word identification.
Yeah. Great, thank you very much. That was a really great presentation. And I think we have used our 5 minutes break already, but I think it was used for a great cause. And I mean, there has been really great questions and great discussion afterwards. So thank you very much again for the very inspiring and great talk. Thank you very much.
Thanks for the opportunity to share. Appreciate it.
I think we can move on next to the next presentation, and I'm delighted to introduce Etienne Bordet he's a professor of human robotics at Imperial College London in UK, and his talk is entitled Cortical Processes of Multimodal Sensory Learning in Human Neonates, which will bring a very interesting perspective to neurohaptics. So the floor is yours, Etienne, please.
I think you're muted.
Thank you very much. You hear me now?
Yes, we do hear you now. Yes, correct. Yeah.
Fantastic, Farrokh. So thank you so much to organize this exciting workshop. So the title is very exciting, and I try to find something that is sufficiently interesting. So let's see whether it will be okay. So let me share my screen. Okay, so you can see my screen?
Yes, we do see your screen, yeah.
Okay, so first so what is human robotics? So basically we use robotics as a tool to investigate human motor control, and we developed robot for humans. So for example, so you have this cerebral palsy individual who cannot use a normal wheelchair, and so we had to develop the human machine interaction so that he becomes able to use a wheelchair. And on the right, you have this hand with 6 fingers, naturally with 6 fingers, and recently we looked at understanding the intelligence of these people, the manipulation intelligence of these people, and we found that basically they are more clever than we are with 5 fingers hands, and maybe the question is why we don't have 6 fingers. Okay, anyway, so let's go to, so the way we work in general, so the main interest is human machine interaction. And so for that, we use whatever is needed to understand it better and to make it work better. So it can be control, psychology, robotics, neuroscience, physiology. So we have fundamental neuroscience investigation using, doing experiment with haptic interfaces in particular. And when we do not understand what we find, we make a model to understand it better, the principle behind the results. And we have applications that sometimes come directly from what we found in the neuroscience, sometimes are done in a opportunistic way. So today I want to speak a bit more general than the original title. So multimodal sensory learning. So first we will speak about, I will speak about fMRI correlate of proprioception in preterm infants, then about associative learning in neonates that we looked up and using fMRI as well. And after I will go to something more traditional in a way, so adaptive with your haptic perceptions that is done without fMRI with haptic interface. So the question of premature birth. So one thing is that the number of premature births does not decrease, and also medicine is improving. The risk of getting cerebral palsy with on preterm babies does not decrease as well. So you have about 10% of babies born prematurely, so with 5 or 6 months or 7 months, who develop cerebral palsy. So this is sensory motor impairment. And what happens is that the first evidence for CP is at about 12 months, so looking at movement, but it's not, yes, it's really a bit subjective still, and you get an accurate diagnosis at 2 years. So 2 years is very long, right? So when you see, so when you have seen the development of your babies, so in 2 years it's happening so much, so you would like to maybe find to be able to act as early as possible so that you may get a window for trying to do something, to make some kind of habilitation, not rehabilitation in the case of children who never had a model for their motor control. So they have to learn with the impairments. And so we want to detect abnormal brain activity, so using functional magnetic resonance imaging and an fMRI-compatible robot. And so this is research that we do for more than 10 years now with collaborators at King's College, so in particular Tomoki Arishi and David Edwards. And this is research that goes very, very slowly because so you have these very fragile babies. So basically, each baby is about the size of my hands, and it's so fragile, and so also these babies, of course, move, what is in principle incompatible with fMRI. So we lose a lot of images from that, and that's something that is difficult, but we like it. So it's not too advised to do for assistant professor, I would say, because you do not get many papers, but it's very interesting. Okay, so you have one of these robots. So you see, it's very simple. Actually, it's soft robotics. So you use whatever material. So you can use Lego components sometimes. You use so it's opportunistic mechatronics. So you really need what you need. You really use what you need for that specific experiment, rather than developing an overall interface. That's not very successful, developing an interface for everything. Okay, so you have to synchronize with the scanner. This is actually relatively easy. And so one of the tricks we had in this robot that was done by Alessandro Allievi. So you see that, so to measure the wrist angle, so he used just a fiber optic. So basically cutting the fiber optic, and then some of the light is going out depending on the angle. So if you have a large angle, more light is going out, and from that you can measure the angle. And so these are the kind of nice mechatronic development. Now, going to the brain, so you see, so this is anatomic MRI. So you see the difference in size of the brain between 28 weeks and 44 weeks. So you see the huge change of size. But of course, I mean, size is one thing, the connectivity is another thing, and maybe much more important. We have to do the basic work. So basically, David Edwards started to work with us because we had experience in MRI-compatible robots, and he had some papers about fMRI activity in preterm babies, but the results were at best conflicting. And so we had to start for a few years, trying to understand what is really happening. So for example, when you take the HRF, so the hemodynamic response function, that is the function from the movement to the brain activity. So you see, so in blue, this is the adult's HRF. In red, the term infant HRF, that is actually relatively similar, just less important response, but a similar timing. And you see that the preterm infant has a much delay HRF. And so it's really important to use the correct HRF, because so you can see this on this activity. So on the left, you have activity using the proper HRF, so for preterm babies, and if you use the adult HRF, you see that you would filter about everything. So this is one thing. So one study that we did recently, so from Sofia D'Alorso, so this is, so we developed interfaces for the ankle, for the wrist, and also for the mouse. And for the mouse, we had ethical problem in the sense that we developed a robotic interface and it was working well, but so you had to maintain it in a mouse, and you are not allowed to put an elastic to maintain it in a mouse. For parents would not be happy with that. So we had to give up that. The only thing you can do is to modify existing tools. And so we modified an air jet that is so sending air to your mouse, and from that we can stimulate the mouse. And so you see the, so this is a measurement of more than 10 children. So preterm babies at 34 weeks postmenstrual age. And you see that basically there is no surprise in the sense that it's about the same organization of the homunculus as in adults. And so it seems that there is no surprise. For us, it was a big surprise because actually it was really an open question in the sense that in other species, so in chicken, for example, when you consider 2/3 of the gestation, then the organization of the brain is not yet there. And seemingly in infant, it is already there. And that's something that has consequences because so if you have a problem at that point, then okay, you may learn differently and so on, but you will not be able to change the organization. So there will be some serious affection depending where it is in the brain. Now, another study that we did also by Alessandro. So we look at the brain, the evolution of brain activity from 6 months, 7 months to 9 months. Of course, it's corrected age because the babies are already born. And so what we found is that first you have contralateral activity, and then you have by about 35, 36 weeks, you have ipsilateral activity as well, and you can study the connections, the establishment of the connection between the two hemispheres. That is quite interesting, and close to term equivalent age, you have kind of pruning of activity, so as if the brain would concentrate on the useful neural network. So this is so this is interesting to see the evolution. So again, we couldn't know how it would be. It was total exploration because looking at some babies, we had again conflicting finding between contralateral and ipsilateral activity, and it's only by taking enough babies that we could really understand the picture. Now, what happens with babies who are affected? So let's consider structural connectivity. So this is a preterm baby who is normal, healthy. So you see the anatomical MRI and you see also fMRI, and basically there is some, so you see the connection. So you have the somatosensory tract that is the afferent tract, and you have the motor tract, the efferent tract. And the way you do is that you find the area you're interested in with an fMRI, and after you look at correlated activity, and from that you can trace the tract. And okay, so now let's look to a baby who had, so you see in the anatomical MRI and in the fMRI, you see that there is a lesion in the brain. So it's an area that has been damaged. And you see that then the somatosensory pathway go around the area of damage. However, the corticospinal tract could not regrow. And then, as a consequence of that, so this child developed, unfortunately, cerebral palsy on the right side, so the side opposite to the affected brain area. So using fMRI, you may be able to characterize better the functional impairments in this infant. Okay, now, so I want to go to multimodal sensory learning in neonates. So the question is that, so you have babies, so at the birth, you can imagine the big change between the mother womb and the external environment. And so the baby has to to understand immediately and to make association in order to understand. So understand is interpreting the world, right? And it's quite important that the baby from the beginning is able to integrating properly. And so the question is, how are multimodal stimuli processed and integrated? And so for that, we use again this MI-compatible robot. We did movement, and we mapped the cerebral cortex processing underlying audio and motor cues, right? So what we did is that basically we have audio cues that are associated to movement, and at some point you have only the audio cues and you see whether there is association. And for that you look using fMRI, you look to the brain. So you have the protocol here. So you see the protocol of 22 minutes, so you cannot make too long. And so you see, so in yellow, you have sound and movement together. And sometimes you have the green, and the green is sound alone. And you can see the evolution in this more than 20 minutes. And okay, so first, so this is at baseline, you have the response to both, to either movement or sound. So you see the areas for the movement and for the sound. Of course, for the sound is in auditory areas. And this is what you find at the end of the learning. So you see on the left in yellow, sound and movement. And when you have only the sound after learning, you see that you have actually a similar activity, and this activity is completely different from the sound activity before learning. And so it's something that is interesting. So it is known actually that babies are able of association. So from the beginning, basically, but it's the first evidence that brain activity level and characterization at brain activity level of this associative learning. And of course, you think that you could use this association then to let this baby learn something, because of course you cannot tell to the baby now you do that and the baby will do it. Actually, you can even not do this with adults, but a bit better than with babies. So you have to find ways, and we don't know ways yet, but we think about this direction of using associative learning in order to condition the baby to do some task. So this was for the baby, and now let's go. So again, so these are few results because you have a lot of work for doing the studies, but the results are extremely simple with this fMRI analysis. Now, I want to consider adaptive haptic sensing. So in adults, so in our typical graduate student population. So you know very well that the nervous system can control the body viscoelasticity to shape the mechanical interaction. So that's basically impedance control. And now what is unclear is how does this viscoelasticity adaptation influence haptic perception? Does it have any influence? That's the first question. And okay, so if we understand how the change of viscoelasticity is influencing haptic perception, could the brain modify the body viscoelasticity to improve the sensing, to improve the perception? So think about this situation. So you have to go down these stairs. So you have full light, so it's no problem. You just go down. Now, what happens when it's dark? Then when it's dark, you will probably take the barrier and help yourself with the barrier. And the question is how you will combine these two different sources of information to understand how the steps are turning down. And okay, so we use this dual haptic interface. actually we use only with one person in this experiment. So it's a very simple whisk interface for whisk flexion extension. And the advantage that it is simple is that you can measure the muscle activity very well. So you can always measure muscle activity, but in this case, you can interpret muscle activity very easily, dynamics are linear, and so on and so on. Okay, so this is the task. So you have to follow a target that is moving pseudo-randomly, and you can have visual noise. And okay, so first is visual noise experiment. So you have to follow the target, that is this cloud with your whisk flexion extension. And what is interesting is that you are related actually to the target via your co-contraction. So that's a function that we manipulate, that we create. So when you co-contract, you are more guided towards the target position. And okay, so and we inject different level of visual noise. So this is in these clouds. So you have visual noise in the velocity of the point, how they diverge from the target position. And we present the noise condition in random condition depending. So each subject has different order of presentation. And so this is what we find. So on the error, so you see that the error is decreasing over the block of trial. And what is interesting is that it's becoming, so at the end of the learning, you see that the error is basically independent on the visual noise condition. Actually, so it looks like the most accurate condition is different, but when you do statistic, you would see no significant difference. Okay, now let's look at the co-contraction. So we measure this EMG and we look at the co-contraction. We see that co-contraction is decreasing, like always when you have learning, but gradually you have a different level of co-contraction depending on the visual noise. So namely, when you have a large visual noise, then you co-contract more. And in a way, it's logical because you know that it will guide you better using this guidance from induced by the EMG, by the co-contraction. Now we conducted another experiment. This is a haptic bias experiment where, in fact, so you are guided along a trajectory that is biased relatively to the visual target, right? In this case, there is no noise on the visual target, but you have this displacement of the haptic feedback. Okay. Again, we use different level of displacement. So they are plotted on the figure. And so you relatively large, from minus 17 degrees to plus 14 degrees in the other direction. So relatively large noise and also little noise. And now what do you find? So we find that the tracking error is also decreasing, but now, so if you have large haptic bias, then you have more error. What happens with the co-contraction? So at the beginning of each trial, you stiffen, but you relax fast, and then you see that again. So the haptic noise induces different level of co-contraction, and in this case, when you have little haptic bias, then you co-contract maximally. When you have large haptic bias, you co-contract, you relax, you tend to relax. Okay, so if we look at this visual and haptic noise experiment together, then we see that with increased visual noise, you increase co-contraction, and with increased trajectory bias, you decrease co-contraction. So we want to understand how we can make sense of these two results. So for that, we used computational modeling. So we started with the dominating model that is just that you would increase co-contraction as response to error. So when you have tracking error, you tend to increase co-contraction to counteract this error. So when you do that, you see a relatively correct trend for the visual noise deviation, but you see that you get the opposite trend for the trajectory bias. So this doesn't work. Now, we can think that basically it seems that the brain is able to understand the effect of the co-contraction. So when you have large haptic noise, then large haptic bias that you want to relax because you want to filter this noise. On the other hand, when you have large visual noise, you try to help yourself with the haptic guidance, so you co-contract. And this we can, so we consider the prediction error, so it's maximum likelihood function. So you have, so you consider both the haptic deviation, so the deviation from the haptic noise, the deviation from the visual noise, and they should combine statistically optimally. And also you have to co-contract minimally. You have to minimize energy because otherwise you would just diverge. And so when you consider that, you see that you get a very good match for both visual and haptic condition. And voila. So that's the conclusion. So that's an interesting algorithm that you can use to interpret all kinds of interactions. So interaction with the environment. We have done an experiment where you can use the same model to understand the interaction with a partner. So when you are connected to a partner, like in dancing, then again, it seems that you will combine visual and haptic information in a statistically optimal way. But the most important of that is that you voluntarily control the co-contraction to change the perception, to improve the perception. Normally, you change the co-contraction just to change the mechanical interactions. Here, you change the co-contraction to improve the sensing. And I will be happy to look at your question. Where's the question?
Thank you very much for this great talk. I think we're running behind the schedule a little bit, but by a couple of minutes. But if there's any burning question that we can take it quickly in a minute or two before we get to the next speaker. Please, Katerina.
Thank you so much. This is absolutely mind-blowing. I could speak for an hour. I'm sure the rest of the meeting feels the same. I think we need to email you to ask you particularly about your last computation with effort and sensory. We have tons of dyadic experiments we can throw at it, so I'm very excited. The preterm study before, I'm so sorry if I didn't get this, but was this a simple sensory association task, or was it statistical learning? And do you think it would apply in statistical learning with sensory motor stuff that you're doing?
So you mean for the association learning? Yeah, so basically you just associate. So, okay, so it's always like that. So association learning, so you have, it's a bit more simple than Pavlov's experiment, but in the same direction. And so it's even more primitive. So you have two stimuli, and when, so you present them together, and then the brain takes the habit to have them together, and so it seems in this case it's building a multi-sensory trace of the association. So
it's just that there's a lot of stuff on statistical learning in preterm infants and young infants, and I think nobody's done it like you, sensory motory. So maybe I'll send you some papers to show you what I mean.
That would be great. I look forward to that. Thank you.
Excellent. Thank you very much. Again, this is really very interesting and very inspiring work. So that was great. Thank you very much. So I think we get to move on to the next presentation, and it gives me a great pleasure to introduce Katerina Fotopoulou. She is a professor of psychodynamic neuroscience at University College London, UK, and she will be talking about the neuroscience of affective touch, from basic mechanisms to tactile emoticons. The floor is yours, Katharina. Thanks again for accepting our invitation.
Thank you, a pleasure. It's really an honor to be in this great company, and thank you so much for putting this together. As you will see, I do quite a lot of work from very different angles for the past 10 years or so on touch, and we've always wanted to link with more haptic researchers, so I'm delighted to finally be here. And also, I am a neuropsychologist by first training, so I used to do a lot of work in neurorehabilitation and stroke, so I got a lot of inspiration already from this workshop. But today, I'm going to try to talk about affective touch, and particularly a specialized affective touch modality. So, you know, in other domains of neuroscience, we have been really interested in pleasure. Think of addiction, think of what we know about hunger and satiation and eating disorders and obesity. But when it comes to the skin, we are, I think, guilty of having neglected the pleasure of the skin. And my screen isn't moving. Why aren't you moving, screen? I haven't given my screen enough pleasure. Let's see. It moved. Yes, very good. So, you know, we tend to talk about what happens in the periphery and how we can divide tactile and particularly mechanoreceptors into different categories, and we tend to emphasize discrimination, proprioception, temperature, pain, and we seem to be ignoring, or at least not dedicating as much science to sensual, affective, pleasant touch. And particularly there's this population of low threshold, slow conducting, unmyelinated axons, the so-called CLTMR in animals, or the CT systems, as you will see in humans, which we know existed in mammals for decades, but we only found out exist in humans in the 90s. And we now know it exists particularly, but not exclusively, in hairy skin. So we're talking about slow conducting, not very efficient for tactile discrimination fibers. And for some bizarre reason, it seems that only the Swedes were ready to talk about sensual pleasure, because this all starts in Scandinavia. So inspired by studies in cats and other mammals, in the 90s, studies done largely by single unit microneurography, so recording from the skin with little electrodes, identify these fibers in the human skin. And subsequent work has shown that they are low threshold. They respond to particular properties of tactile stimulation that I'll speak about in a moment. And they have these relatively small and patchy receptor sites all over hairy skin. I don't think receptor sites have been studied in glabrous skin. And they're sort of like you see them there in that picture, sort of roughly round and oval. And this kind of fibers respond optimally to forces that are not, you know, too strong or too soft. And most importantly, their mean amplitude is optimal when you stroke the hairy skin at speeds of between 1 and 10 centimeters per second. Anything slower is actually dropping their mean firing frequency, and anything faster does the same. So contrary to what we know about other fibers, they don't have a linear relationship between activation and perceptual also intensity, but rather this inverted U. So based on velocity, the mean firing frequency shows this inverted U, but also behaviorally, in now more than 100 studies, we see similar results in terms of perception, and therefore a correlation between the two. And in terms of central processing sites, well, there's a lot of neuroimaging studies now, both clinical neuroimaging studies in patients with neuropathies, peripheral neuropathies, as well as you will see now some central evidence from us, showing that contrary to other tactile fibers, there may be separate pathways for this system, that conclude in the posterior insula rather than classic primary or secondary somatosensory areas. And there is also some nice neuromodulation studies showing that, for example, if you inhibit the primary or in another study, the secondary somatosensory cortex, you get reduce of tactile intensity to this kind of stimulus, but not pleasantness. And they've tried to use coils that will capture deeper in the brain, the insula, but actually based on all of these neuroimaging and neuromodulation studies, we have no evidence or causal evidence up until recently that this is the final or the first, if you like, central representation of this system in the posterior insula. So we tried it with stroke patients, right hemisphere patients. We did standard gentle stroking manually in the arm, in the bedside, and then just analyzed their lesions in 60 patients with right hemisphere and no vision. And what you can see very quickly is that indeed, even when we don't take the people who we could guarantee they have intact some conscious perception, but everybody, you get a distinctive lesion in the posterior insula, explaining the lack of sensitivity to gentle touch in the contralesional arm. Interestingly, when you look at people who lost their affective touch sensitivity at the ipsilesional arm, you then see that that is explained by lesions in the anterior insula. So this is consistent with what we know from other studies in the interoception system, as I will talk about in a minute, that show that maybe signals go from these peripheral pathways to special parts of the thalamus to posterior insula first, and then for reprocessing at higher levels to anterior insula, which is what we may be seeing here. And this is really Craig's 2002 onwards story. So according to this, contrary to classic knowledge about touch, there is a lamina 1 pathway that is closer to what we know about visceral pathways. So according to Craig, we should really stop thinking that all temperature and pain and each perception or sensation on the skin should be classed under touch, and at least some of it, the one that has affective value, and we think goes from lamina 1 to medial thalamus to posterior insula, should really be part of a new definition of interoception. So according to him, it's a new sentient pathway for how we feel, not about the environment, but about our own body. So the same as how we feel about our heart rate or our respiration. And that is a concept of affective touch as part of interoception. So this is the idea that we have at least two broad systems, one interoceptive, affective with these slow conducting fibers versus the fast classic discriminatory systems for touch, one going to posterior insula, the other going to somatosensory cortex. And that generated quite a lot of interest in neuroscience and related fields, spanning from cellular level analysis all the way to lifespan studies, and it's still going. So in London at UCL, where I work, we founded the International Association for the Study of Affective Touch that actually met yesterday, trying to complement what's been done in the International Forum for the Study of Each and pain. And there's more and more interest, and this is a little bit of what I'm presenting. So if we think that neuroanatomically, neurophysiologically, this system exists, what does it do? At the end of the day, we have A beta afferents that are capable of encoding velocity information and faster and better. So why do we have this special and slightly non-informative slow system? So the classic idea from the Swedes was that maybe it's responsible for salience. So yes, we can pick socioaffective information about the body from others, but maybe we need to pick it with some salience to distinguish it from the rest of the noise. And us and others have developed this into broader theories about how these modalities may contribute to homeostasis. And so, for example, during multisensory integration, some of the sensory learning we just heard about in infants, we know that other people can act as effectors. So I have a homeostatic need. Let's say I'm hungry, then my mother feeds me and strokes my back. At that moment, that downregulates my hunger and down-regulates relative emotions. So there we have a kind of effective regulation as my embodied needs are being met. So we've done quite a lot of work on multisensory integration and that, but I don't have time for everything today, so we might leave that for the discussion. We also think that more than just being simple effectors and homeostatic regulators, social touch, and particularly CT system-based touch, may contribute to more predictive model-based ways of physiological regulation. So what we call and others call social allostasis. And so I'm going to very quickly go through our work on how this kind of touch may modulate. First of all, we've shown that CT optimal touch is better than other types of effective touch to communicate emotion, even when you have no other cue. But we've also shown that it regulates affect, particularly decreases negative affect and increases positive affect. And I'm going to show some bizarre studies of how we go from that to haptics and soft robotics. So why, how can I summarize this? Well, it's something that it's well known in neuroscience, but it frequently, and in psychology, and it frequently gets really, really confused. So I'm just going to repeat it for the sake of being dumb, but I really think it's useful. Human infants are born without the ability for purposeful movement. So there's a lot of stuff on attachment theory and the implications of this and our fundamental love for other human beings. But at the more sort of mechanical level, something important is forgotten. And that is the following. Infants cannot survive, and that means they cannot establish homeostasis. And that means they cannot regulate their interoceptive modalities in any way without touch. There is no way for an infant to change their thermoregulation or their hunger or their satiation or their thirst without somebody bringing the bottle. So that means without touch, no homeostasis. And there is simply very little tracking the implications of that in brain development. So we've started that some time ago. And so like other mammals, indeed, we have a social attachment system, and we have very strong, possibly co-opted systems like the pain, the opioid-based system to support social connectedness. Yeah, nothing I said about homeostasis takes that away. In our sort of more Bayesian thinking, attachment can be thought of as a first prior. So when you fulfill attachment, when you have touch that signifies the presence of a caregiver, this downregulates some social anxiety, stress that is innate. But that doesn't mean that other homeostatic and allostatic functions aren't being accomplished. So separation hurts, even in adulthood, rejection hurts. And increasingly people have understood that at the homeostatic level, maybe with opioid modulation, but also allostatically with oxytocin, and we do some work on that. And there is wonderful, from Mimi's lab, for example, wonderful data on lots of things like HPA axis, epigenetic effects, etc. on this. So we know that if you deprive animals from co-specific touch, specifically more than social presence, they will become faster, much more ill, and they will die younger. And if you provide co-specific touch, particularly maternal touch, these effects will be reversed. We know that for a long time in animals. We're starting to find out in humans, and we think the CT system has a special role in this. And so we call that mechanisms of comfort. And so we bring people in the lab and we do all sorts of experiments as well as EEG studies. And we've shown yet again that a slow CT optimal tactile stimulation is better at downregulating pain and related salience, insular and anterior cingulate brain sites than non-CT neutral touch. And this seems to be linked also with oxytocin. And pets, we find that pets work better than even friends. So we're looking more into that. But all of this that you can read about in the literature from us and others is relatively short term for obvious reasons. We cannot deprive human infants for co-specific touch for a long time. And then COVID happened. So for us interested in this, COVID was an unfortunate opportunity. So, for social safety, we were asked to social isolate, and they call it social distancing, but given social media is actually physical distancing, and it's mostly touch distancing. So we were very lucky at the time. We were invited by colleagues to run all sorts of huge surveys on it, which I won't present. I'm a questionnaire snob, but I end up having lots of data from these surveys. But some very interesting things relate to the technology of touch and what we can do with this CT system. So I wanted to bring it here. So very quickly, for example, if you just sample people's appreciation or attitude or perception of how much they think the lack of touch over and above other life conditions in the moment influence their mental health, you will see that intimate but not friendly or professional touch seems to have a greater effect. So the more of intimate touch you had recently, the less the anxiety, the less the loneliness, the better the mental health, and the better the ability to tolerate the isolation, and vice versa. But obviously, what about people that don't have intimate touch at home during the pandemic? So one thing we did in this survey is we took advantage of simple vicarious effect in neuroscience. So this is the idea that once we've learned a certain modality such as touch, then similar but not identical brain areas are activated when we see touch, for example, or it can be another cross-modal combination. So this is a kind of tactile empathy, people call it, for lack of better terms. And we know, and other people have shown since 2016, I believe, that there is the same kind of vicarious effect for CT optimal touch. So just seeing gentle stroking of somebody else's arm activates your posterior insula. So what if we show isolated people videos of intimate human to human, human to pet, and human to robot touch? Simple videos. People sitting at home, again, terrible selection of findings for the interest of time, but basically overall, all vicarious touch had a positive effect to pre and post that mood and stress ratings. But pet videos were consistently found to be more soothing, and also people had all sorts of attitudes about this, saying that it was easier for them to accept it, much more than robotic touch, which we have some work to do. I have more data to show you if interested. And of course, all that raises the issue of digital communication. So I trust that most people in this workshop know more about this than me, but most of our social media communications are auditory and visual. And we're touch researchers, we can't have that, particularly since we've spent a lot of time saying that if you're going to have one modality only for some reason, you're blind or we blindfold you in the lab, affective touch, particularly CT optimal touch, is a better modality to communicate emotions like social support and other pro-social emotions. So what is the effect of social media of not having this touch? And what would be the effect of using technology, as we've heard before, to add not just touch to our tactile social media interaction, but affective touch, and particularly CT optimal? So there's quite a lot happening. I'm sure they'll be pretty in parallel workshops and starting at the conference tomorrow. But there's very little, if anything, in fact, testing CT optimal touch. This is a very simple experiment we did with a student just before COVID, actually. So we created a fake Twitter-like environment where people could imagine that they're posting these kind of tweets or posts. I was made redundant. And then we get either classic visual emoticons or a combination of visual and tactile emoticons, or just tactile emoticons. So tactile emoticons will simply be instances where a person or a robotic device will stroke you in CT optimal or non-CT optimal velocities. And obviously we did this in all sorts of combinations of vision, no vision, etc. Very quick data. Again, this is preliminary, and this is for the manual only. So the robotic was felt as a bit awkward, but the manual shows a clear advantage for tactile over visual and for CT optimal tactile over neutral. And we are continuing this work. There's a nice presentation by Caroline van Zengt in the main conference around using her soft robotic device and EEG measurements, looking at this kind of work. So looking at the perception of the device, but also we're continuing with what is the effect of adding such wearables in social media communications. And we've also, with other teams at UCL, developed a connecting mittens where we don't just have an interface, but we can have direct communication between two long-term parties. And again, trying to simulate the properties of CT optimal touch where possible. So very briefly to conclude, neuroscientific, experimental, and now naturalistic findings converge on the role of the specialized tactile pathways on affect regulation and cognition. The CT system is definitely not the only modality for affective touch, but it's a very good one. And technology, I think, can work closer with neuroscience and psychology in this respect, to design and apply some of this insight in the real world, both therapeutic and just pleasure-based world. But we need to look at this system as well as other existing knowledge about touch. And thank you to all the wonderful researchers and collaborators, funders, and you for your attention.
Thank you very much. This was really great, mind-blowing research. I personally, I'm very interested in this, and I can ask you questions until tomorrow. So thank you, but I think I'll give space for the audience to ask questions, and I think I'll start with the first question by Etienne. So I think, Katerina, what do you know about the development of discriminative touch, whether there is the same difference in infants?
The same difference as in what? Sorry, I didn't understand that. The same difference as in?
Yeah. Well, maybe, Etienne, you can unmute yourself and you can elaborate more about your question.
I mean, the same difference between affective and discriminatory, or in other terms, how early does, I presume this is the question.
Yeah,
how early,
maybe, yeah.
Do we know if there's a differentiation, or at least if there's a presence of this kind of CT optimal affective touch in infancies? Yes, we do. There's now 4 or 5 studies looking at both the direct perception and some learning effects that I think you will like, Etienne, of specifically CT optimal versus not touch in infants. So, for example, Italian colleagues at Teresa Ferroni's lab have looked at, there's an effect in young infants that they can learn face recognition, but if the face they're looking at, whether it is a real human or a robotic avatar, is looking directly at them versus away, the direct gaze, kind of second person cognition because of the dyadic element, is leading to better face recognition. So they replicated this, but also added affective touch to this experiment. And they showed that affective touch both can substitute the direct gaze effect, and when it's present at the same time, enhance it. So they also think that affective touch is not only, like other infant studies suggest, a affect regulator in the homeostatic sense, but as I've tried to say, it's also possibly leading to epistemic gain. It's a learning facilitator. So again, this idea that it's really modulating salience, or computationally, we would probably say precision.
Yeah. Thank you very much. And I think there's another question also from Preeti. And do you think adding haptic modality in social media could make it more addictive and probably have a counterintuitive effect?
Yes. I think the more modalities we enter, the more naturalistic we make our VR or social media or other gaming experiences, the more danger in that sense they become. But I'm not one to worry about this. This is, actually there's 2 things to say. So if we overdo it, then there is always that awkwardness or uncanny effect. But within the realms of not creating something too realistic, but creating something immersive, I think, yes, it has a greater hold on our psychology, and there is sufficient evidence for this. But it never has a hold beyond what other social and non-social activities would have. It depends on both dispositional and constitutional factors. So it's not the technology's fault.
Yeah. And maybe I can ask one question, as I don't see more questions on the chat box. And I wanted to ask about the findings related to EEG studies, given that you're looking at the insula area and maybe the amygdala areas, which sit really deep in the brain. And what we know about EEG is that they measure kind of subcortical or surface kind of electric activities. So I wonder how you managed to get that deep inside the brain to measure those kind of activities. Yeah.
Yeah, so there are a few EEG studies on affective touch and some in infants who claim to see things in theta or even gamma, but this is not something we've done. What we've done is we use the EEG to see how affective touch stimulation downregulates well-established signals in the noxious stimulation range. So we're looking at N1 and P1, P2 potential. So we can capture the insular and anterior cingulate there. So because they are, the noxious stimuli are quite salient. So that's.
Yeah, indeed. Thank you very much. I really thank you for this really inspiring talk and all the speakers and I think we deserve to have a few minutes of a break now. So I think we'll be back at 11:30. So we can have about 5 minutes where we can stretch ourselves, maybe take our biological break, and then we come back. Thank you, everyone.
Okay. Thank you. Okay, so I think we are ready to resume. Yeah, yeah, you can start sharing the screen. I introduce you, and then you can start the talk. So, hello everyone. Again, welcome to the second half of the workshop. It has been a great day and great event. A lot of amazing presentation and talks. So thanks again to all the invited speakers. So it's my great pleasure and great honor to introduce Ilana Niski. The topic of Ilana's talk is integration of kinesthetic, tactile, and vision information in perception, action, and adaptation. And Ilana is from Ben Gurion University of Negev from Israel. And thanks, Ilana, again for accepting our invitation and sharing the amazing results of your research.
Thank you very much, Farouk. And again, thank you for organizing the workshop and inviting me. And it's been a really eye-opening experience so far. And yeah, so this is of course not the view I see from my window, but it's not too far away from where I am at right now. So anybody interested in this kind of view, hopefully after the pandemic ends, you're really welcome to visit. So I want to talk to you about trying to understand the integration of different sources of information in our perception, in our adaptation. When we're thinking about haptic interfaces, so traditionally and classically, we are using kinesthetic devices that actually apply forces on users, and they're widely used in many applications and also in research. But recently, there is an increasing interest in tactile interfaces that stimulate the haptic system, the somatosensory system, but without applying net forces. And these have been really, really successful in conveying all sorts of information. So together with my colleagues from back at Stanford, we studied their effect on perception of stiffness and teleoperated palpation, in guidance of motion, in discrimination of direction. The group of Marcia O'Malley has done really beautiful work on using tactile devices for substitution of proprioception and conveying the kind of information that we just saw in the beginning of the workshop. So these are really exciting way of communicating with our sense of touch. And what we are interested in, together with a few of my students in the lab, are trying to understand how exactly the different sources of information that are coming from the skin and from the deeper sensors may be integrated. And the approach that we're taking is sensory motor control, kind of computational motor control approaches. And these are the stories that I will tell you right now, focusing on the effect on perception, so very basic psychophysical studies, perception on stiffness, the control of grip forces, and hopefully if we'll have time, a little bit on force field adaptation. So first of all, okay, yeah, so first, let's focus on interaction with elastic objects. And this is the work led by Mo Farajan, a PhD student in my lab in collaboration with Hannah Kasowski. And they asked participants to interact with virtual elastic objects. As you see in this video, there's a participant interacting with a robotic device that applies forces that are opposing the motion of the participants and interacts with the force fields. Now she's holding a skin stretch device, and in some of those trials, a tactor, which is the red dot that you see here on this image, is actually applying a stretch to her finger. So the way we analyze the results of these studies is that we ask participants to compare pairs of elastic objects, and then we compute psychometric curves that are the probability of responding. One of the objects has higher level of stiffness, and if one of these objects has stretch and the other is not, we will see a shift of the psychometric curve, and it can be quantified by the point of subjective equality, which is the point where both objects are perceived as identical. And with these experiments, it was known from before, but we reproduced this result that stretching the skin causes an illusion of touching a harder object. As you can see here, the positive PSE, the larger the tactile displacement is. Apparently, this effect is immediate, so it's almost really an illusion, and the size of the effect does not depend on whether the probing was restricted to only one probing or free probing. And what was really surprising to us, that also the just noticeable difference, which is the measure of the sensitivity, essentially the slope of these psychometric curves, was also not different between one probing and free probing. So apparently, if you ask participants to interact with objects, they will probe them several times, but they don't get, at least not something, don't get additional information from this additional probing. Mo also looked at the effect of visual feedback on the skin stretch illusion. So she performed the same experiment, but in one of the conditions, there was no visual feedback. So the same version of the experiment as the one I just described. But in the other case, participants also saw a visual deformation of the cube. And our hypothesis was actually that this additional visual information will leave less space for integration of the kinesthetic and the tactile information, and that this should weaken the visual illusion, and the illusion due to stretch. And this was indeed the case. So here you see again these psychometric curves. These curves in the middle are ones without a stretch. A shift to the right indicates an added effect of feeling a harder object, and the effect was smaller in the presence of vision, and this was consistent in all the participants. Although what I want you to pay attention to is that these perceptual effects are highly variable between participants. So if this is the average effect, if we're looking at the delta PSE, this effect of feeling a harder object. So here the condition, the first two on the left are without vision, without stretch, with stretch. You can see that some participants are almost not affected by the stretch, whereas others are very much affected by the stretch. So these are the perceptual effects. The next question Hannah asked was, well, it seems like there is some sort of integration of information here, and a simple model that actually weights kinesthetic information with cutaneous information predicts this illusion of touching a harder object. But the question was, this linear weighting, what is the source of the weighting? I mean, what determines the weighting? How the weights are determined? And our hypothesis was that actually, as in many examples in sensory motor control, this weighting may be statistically optimal. So similarly to how we know that the nervous system combines visual and haptic information according to maximum likelihood, weighting the more reliable cue stronger than the less reliable, but nevertheless not throwing away information, we thought that maybe the same thing happens in the integration of kinesthetic and tactile information. And then we thought, well, if this is the truth, if this is the case, we can try to increase the uncertainty of either the tactile or the kinesthetic information. And then if we increase the uncertainty, we will increase the variance in perception and decrease the weight. So Hannah designed these predictions. We already saw that the just notable difference is not supposed to be affected by the fact that we're adding skin stretch. And if we introduce kinesthetic uncertainty, we should increase the JND or the tactile uncertainty. And then the effects on perception would be that if we have a certain increase in PSE indicating perception, the illusion of harder objects, if we increase the kinesthetic uncertainty, according to maximum likelihood integration, we should see an increase in this effect. And if we increase the tactile uncertainty, we should see a decrease in this effect. Why is that? If I'm increasing the tactile uncertainty, I should trust the tactile sense less. And that means that the weight of the tactile information should be lower and the effect should be lower. Okay, so if we're clear with the predictions, Hannah really tried hard to introduce uncertainty in the tactile sense, which unfortunately was actually not so successful. So one way that she tried to introduce this uncertainty was by saying, well, let's have the tactor have added noise. If we see here an example of the skin stretch that was supposed to be applied during a single probing without noise, if we now add some very high frequency noise, so if this is the simple stretch, here's the stretch with the noise. And she did this experiment, and what was really disappointing was the fact that the just notable difference, the measure of the uncertainty, was identical no matter how much noise was induced. So there was increase in JND due to skin stretch in her case, and slightly more increase due to noise, but not something that could be statistically differentiated. And indeed, in her perceptual results, there were also no differences, but this was not surprising because if we didn't succeed to induce uncertainty, of course, we don't expect any differences in the effect. So for now, skin stretch with and without sinusoidal noise still had this very robust illusion of touching a harder object, but we couldn't say if it's optimally integrated or not. So then she changed an approach and she said, well, let's try to introduce uncertainty by not introducing noise into every single interaction, but by changing the information that is presented between the different probes. So imagine you're touching the same object several times, but then every time that you are touching it, you feel something slightly different. And we could use this approach either in the kinesthetic information. So again, having the robot actually apply a different force in response to the displacement every time. So have different elastic objects essentially presented at each probing. And similarly, we could have the same kind of between trials variability only in the tactile case. So let's see what happens here. So here are the just notable difference results and the point of subjective equality results. So first of all, skin stretch and kinesthetic variability increase uncertainty more than skin stretch alone. This is the difference, between the green and the pink bar here. And skin stretch with and without kinesthetic or tactile variability increase the perceived stiffness. This was for sure. But what about our prediction? So first of all, we expected that both the kinesthetic and the tactile variability will increase GND. Well, what happened in reality was that the kinesthetic variability did increase uncertainty, but the tactile variability increased it, but not statistically significantly. So again, we seem to be failing to introduce uncertainty by changing the tactile information. Whatever happens, it's enough that you apply the skin stretch. At least in the way we tried, we were not able to introduce more uncertainty by changing something in the tactile information. We're still able to increase, and again, of course, if we didn't increase the uncertainty, we can't say anything on the perceptual and the bias results. Now, for the kinesthetic case, we did succeed in introducing the variability. So again, this was really similar to the maximum likelihood predictions. We increased the uncertainty, and now we can look at what happened in the perceptual results. But what happened in the perceptual results was the opposite from what was predicted by maximum likelihood. So when the kinesthetic information was less certain, the weight of the illusion was actually less. So what do we take from this part of the story? First of all, it is very clear that adding artificial tactile feedback to kinesthetic force creates an immediate illusion of touching a harder spring. The visual feedback decreases but not eliminates this illusion, but it seems that this illusion is not a result of maximum likelihood integration, and we're still not sure what is the mechanism of integration of information, but it seems not to be maximum likelihood. Now to the second part of the story, the control of grip force. So when I'm talking about the control of grip force, this is the force that we apply with our fingers perpendicular to the object that we hold. And this is the force that is essentially responsible for creating the friction that is needed to prevent the object from slipping. Now, we know that in sensory motor control studies, this is a window to our brain's prediction of the forces, because we know that this grip force is modulated with anticipated load forces that are acting on the object that you're holding. So here is a very classical picture. These are several interactions with that same elastic object from that same data that I presented before, the psychophysical data. And we can see here in dots the load force, the actual force that was applied on the participants. So here we see 7 probings. In red, you see the grip force. So the grip force is modulated in anticipation of the load force that is created. And we know that this modulation does not depend on the actual force acting, because if we would introduce sketch trials, you will see them in further in my talk. If we would introduce trials where no load force would be actually applied, this modulation would still exist. It's predictive. So let's see what happens now when there was actually a stretch. So here for the strongest stretch. So again, the dotted lines are the forces that were applied. The blue is the stretch, the movement of the tactor on the finger, and the red are the grip forces. And we can see an interesting result. First of all, it's clear that with repeated interaction, the grip force increases. The other thing is that something weird happened to the timing of this grip force control. So our first point was to try to quantify that, and we can quantify the modulation by looking at the peak grip force divided by the peak load force, just because this is interaction with elastic objects, so we can't really look at just the forces, it's really the relation to the movement that was made. And we can see here in green the first probing movement, so here the first one, and in blue the last one, as a function of the tactile displacement gain. So no stretch here, and increasing stretch as we go rightward. And what we can see is that really with repeated interaction, first of all, overall the grip force load force ratio reduced, which is something that we know happens because you already know what kind of object you're interacting with, so you reduce a little bit of the safety margin. But what is really important that there is a relationship, an increasing effect of the stretch that was not so strong in the first probing. So there is some component that affects the predictive control of grip force that is developing. Of course, we wanted to look a little bit more carefully into this. So we designed an experiment where we were focusing on analyzing the grip force, and we separated the movements. We wanted to each movement to be separable, not really natural probing, but kind of to see exactly what happens before each probing and after. And also we introduced catch trials. So catch trials are trials where actually no stretch is applied. And and in the sketch trials, we can tell what was the planning by the sensory motor system of the user, not a result of the reaction, but only the planning, because no actual stimulus was applied. And we made sure that we have catches in the beginning of the interaction and at the end of interaction. So here is an example of how a typical trajectory looked like. What was interesting here are a few things. First of all, you can see that there is a weird reduction of grip force at the peak of the load force that we're still not sure if it's an artifact or actually a reactive response to the stretch. It's probably a combination of the two. But what was really interesting was what happens in these sketch trials, and we analyzed them by computing the regression between grip force and the load force. This is a common technique of identifying, of separating the contribution of a baseline safety margin that you apply on the grip forces compared to the predictive, and this is what you see from the intercept of the slope, and the predictive modulation of grip force. So this is the change in the grip force in anticipation of the load that is going to be applied or of the stretch that is going to be applied. And what was interesting here is that the intercept, which is the baseline effect, showed very small dependence on the gain, some dependence on the gain, and overall it decreased between the second and the last probing. So you became again more confident about what's going on, and you reduce a little bit this safety margin. But the predictive modulation of grip force in anticipation of load force was dependent on the skin stretch. And in some sophisticated analysis based on the grip force that is applied exactly when the forces are starting to act, I will not go deeply into this analysis, but this is a different kind of analysis that allows us to see what's happening in all the probing movements. We see that indeed there is an immediate increase in grip force that is not predictive, but then gradual increase in the predictive modulation of grip force in anticipation of the load force. This is the one that is important. So for the lower skin stretch level, there is a slight increase and it stays the same, but for the larger one, it takes about 3-4 interactions to build this internal representation. So the conclusion here is that adding artificial tactile feedback to kinesthetic forces creates, of course, this immediate illusion of touching a harder spring. And the predictive grip force load force modulation changes as a function of tactile displacement gain, indicating the participants actually change their internal representation as a result of this stimulation. And the perceptual illusion, which happens in just one movement, does not depend on this internal representation change. So I'm looking at the clock and I see that I don't have time to talk about this study on force field adaptation. So I will just give the recap, what we did and what was the conclusion. So what we did was really to try to do classical force field adaptation studies, but with the skin stretch added in a direction that is perpendicular to the movement, not like in the stiffness perception experiment. So participants were making a movement in this direction forward. And there was a force that was applied by the haptic device. This is work by Chen Avram, another PhD student in my lab. And the device could apply force to the side. This is in this condition. Participants move from start point to an end point. And then there could be a stretch that is applied in the same direction as the force field or in the opposite direction. And we use force channel trials in which no force was applied and no stretch was applied, but in fact, participants were forced to a straight trajectory to measure what are the anticipatory forces that they apply to cope with this perturbation. And to make the long story short, there were no differences due to skin stretch in the movements that the participants made, in the trajectories, but there were actually differences in the predictive manipulation forces, and there were effect on grip forces. So I'll skip to the conclusion, but I would say that skin stretch in the opposite direction of the force that leads to better representation of the perturbation than in the same direction. And we think that this may be related to some guidance cue that the stretch is presenting to the users. And the group with the skin stretch in the same direction applied more grip force per amount of load force, both in the anticipatory and in the response to force field without increasing the baseline. So the take home from this one is that the tactile stimulation affects adaptation to perturbing force fields. This is in contrast to some previous study from other groups. And I want to add some caveat because this is a result we were quite sure about, but Chen actually performed follow-up studies and done additional versions of probing adaptation in different protocols. And we seem to be having very confusing results on this sense. So we're still trying to make sense of what happens. What are the different ways that stretch in different directions are integrated in this force field adaptation. So I hope in a few months to present a better, more coherent view of all this data and better understanding. But what is really clear is that this information is integrated in force field adaptation. And kind of our conclusions are the open questions in my thinking about how do we really understand this integration of tactile and kinesthetic stimulation is that we understand that artificial tactile stimuli cause immediate perceptual effects. They affect the perception of mechanical properties, but we still don't have an answer of how really this information is integrated. And maybe there is a component of also some kind of explicit, very cognitive, illusory effects that we see them both in the interaction with the elastic objects and also in adaptation. And they are helpful in updating, and the tactile cues are helpful in updating internal representations, but we still don't understand the mechanism, and for some reason they don't change the movement trajectories, and we still don't understand why and how. But again, we have some ideas for modeling that I hope that I can share in the near future. And these are the students that done all this work, Hannah, Chen, and Mo. So thank you very much.
Thank you so much, Ilona. It was an amazing talk, and I personally enjoyed very much. There was a lot of amazing research and great work you've done. So I have some questions, but I think there's also some questions in the chat box, so I'm gonna check them. So Muhammad asks, very interesting and inspiring. Did you explore any gender or age group differences with the stiffness perception study?
So we never looked at differences in age and gender, but I can tell you that I think that is worth waiting for next week, because there is a study that is linking geometrical properties and mechanical properties of the fingers of users on haptic effects, not studied by my group. I was really just inspired by reading the paper. And again, we never looked at age differences just because these participants are all young university students. But I'm absolutely confident that the mechanical properties of the skin do have an effect here. I also think that it's not only the mechanical properties. So it's not just how the skin complies, because I think there is just general sensitivity, almost even how much attention do you pay to this thing. So it's almost sounds to me like the quest of studying the intensity curves of sound perception. This is the direction of thinking that I have about this. And then if you think about this for devices design, I would also think that similar to how in many devices we have a knob for intensity of audio, I think that maybe haptic devices should have one of these knobs as well for tuning how strong do you want the device to act on you.
Okay, that's perfect. So we can, I think, take one more question from Marcia in the chat, and then we go to the next speaker after that. So Marcia asked, Ilana, great talk as always. Could you talk about the perception of a skin stretch activated in different direction? With our own studies, we have noticed that many subjects cannot distinguish between a skin stretch direction when we activate with the rocker. Can you describe your actuation mechanism of a skin stretch?
Okay, so I hear here two questions. One of them is the actuation mechanism, and the other is the different directions. So thank you for this question. So we were fascinated about this question as well. And actually next week, I have Mo will be presenting a work in progress paper focusing specifically on this direction. And I'll do a little spoiler because it seems that there is a huge variability on the effect of the stretch on the different participants. For the first time, we even saw a negative effect of stretch, kind of showing that even if I apply stretch in the same direction as the force field, they may have actually some negative effect. And it seems like when you compare the positive stretch and the negative stretch, there is, between these two effects, there is a difference that the positive stretch is toward higher stiffness than the negative stretch. But then each individual can be placed everywhere on the spectrum. Like you could have strong effect of positive stretch and weaker effect of negative stretch. And then someone can have a strong negative effect of the negative stretch, and it can be all over the place. So it's kind of really new results. I still can't wrap my head about what is the process there, but it's really interesting what's happening in the negative part. About the mechanism of actuation, do you mean like the device? What is the, yeah. So this is the same device that was used in the studies from the group of Alison Nakamura and Will Provancher. So it's a tactor, the Lenovo cap thing that is actuated with a single motor with pressure against the aperture. We are now looking in a completely different application on a device that is kind of inspired by your rocker design. We didn't try it on the fingers, but we're actually using it on a different wearable device. So I think that hopefully in a few months we'll have some results with that as well. But so far all our studies were done with the tactor with the aperture. Yeah, it's really important point because I think there is something about the contrasting tactile forces between the aperture and the tactor that may explain some of the phenomena that we see here.
Okay, thank you so much, Ilana, for a great talk again. So I think we can move to the next speaker. So our next speaker is Preeti Raghavan from Johns Hopkins University. And the topic of Preeti's talk is on role of sensory information in motor recovery. So again, thanks Preeti for joining us. It's a pleasure to introduce you and it's a pleasure to have you here. And the stage is yours.
Great. Thank you so much, Farouk and Mohammed. It's really a pleasure to be here and to hear all the wonderful talks. So I am a physician, a scientist, and run the Motor Recovery Research Lab, where we've been studying motor recovery after stroke primarily, but also after other conditions such as multiple sclerosis. So my focus as a clinician and a researcher has been on how, what is critical to facilitate hand function. You and I know that we grasp objects of various shapes, sizes, textures, and weights, and we do it so effortlessly. We are able to adapt our motor actions based on the sensory properties of what we feel. After a stroke, Unfortunately, a large number of patients have impaired hand function. In fact, more than 80% of survivors cannot use their arms and hands as before. And it's extremely disabling even if you have the other hand, because as you just see, this gentleman, he's using his good hand to hold the cane. So he really doesn't have a hand to do activities with. Now, a stroke is caused by damage anywhere in the brain, but the disability is often caused by damage to the corticospinal tract, which originates in both sensory and motor areas. So the sensory areas are right behind the central sulcus, and you see that in the lateral and the medial view. So knowing this, it's very interesting that a number of algorithms that talk about prediction of recovery focus exclusively on assessment of motor function, right? So for example, there's the PREP2 algorithm. PREP stands for predicting recovery potential. And basically this algorithm can be implemented within 3 days after a stroke, and it predicts recovery at 12 weeks. The basic aspect of this algorithm is the SAFE score, right? The SAFE score stands for shoulder abduction and finger extension. So basically, if you have a cumulative strength of greater than 5 on day 3, then you have a chance of excellent recovery predicted by the Action Research Arm test. But this algorithm is only 78% accurate in predicting excellent recovery, right? Now, if you don't have shoulder abduction, finger extension, then you can do TMS. You can look for motor evoked potentials. Again, you're stimulating the brain and you're looking for the integrity of the motor pathways. No one is really looking at sensory pathways. Right. So we're missing a huge element of what is critical to recovery of hand function. And I think we can do much better. So the question is, how do we really get from, severe deficit to flexible hand function? Can we get there? And so I just want to say that I'm really talking more about these people, who are predicted to have good to excellent recovery. But their prediction algorithm does not involve any sensory aspects, right? So can we improve so what role does sensory information play in motor recovery? So clearly, first we need to define recovery. And it's been defined already for our field as restoring the ability to perform movement in the same manner as it was performed before the injury, which requires not only motor output, but clearly shaping that motor output based on the sensory features. So the features that the discriminative features of touch, particularly obtained from tactile and proprioceptive input, and how it is integrated with motor output. So we have measured sensory motor recovery using an instrumented grasp object. It's been used since the 80s by Johansson and Westling. And here you can change the weight of the object and you can change the texture at the grip force interface. And what you're able to look at is a very fine temporal resolution of all that is happening before you actually lift the object, right? So I'll be talking about this in a little bit of detail, but these lines here represent, line 1 represents touch, line 3 represents lift. And there's so much rich information that we can gather from what's going on in between. So for example, if you look at healthy individuals and you give them two different object weights to lift, you find that both the grip force, that is the force that is normal or perpendicular to the touch surface, and the load force, which is tangential, they both increase and they scale to the weight of the object. So for instance, for the lighter weight showed in the dotted line, the rate of change of load force is lower. The rate of change of grip force is also lower, right? Now, what's really interesting is that even if an individual practices the task with one hand, but lifts the object with the other hand for the first time, you see the scaling. Usually, the very first time you lift these objects, you may not see the scaling because it's learned. It's really the matching of the output with the input. So one question that we had was if this is true. So basically, there's some transfer of sensory information from one side to the other, right? And neuroscience literature has shown that sensory input from one side, one hand, goes to both sides of the brain. So the question was, could we really exploit these pathways to see what happens in patients with stroke? So in patients with stroke, with the affected hand, so these are patients who are relatively high functioning, they can grasp and lift an object, but they don't seem to do it very well. In fact, they don't use that affected hand. And you see that they are not able to scale their force rates with the affected hand. However, when they perform the same task with the unaffected side and then with the affected side for the very first time, you see force scaling. Okay, so this was very interesting. And we asked, so in these studies, we kept the tactile interface constant. Okay, and now if you look at studies where you keep the weight of the object constant and change the texture, then you again see that with normal tactile input, healthy people scale their grip force rates. So they use higher force rates for a smoother object and lower force rates for a rougher object. Whereas if tactile input is blocked, so for example, we applied Tegaderm, then you don't see that, okay? And in fact, one major question was, is there do they scale in a proportional manner? And is there a constant rate of scaling across individuals, right? Now for weight, it's fairly easy to find the relationship, but for texture, it's not quite easy because the rough textures and the smooth textures tended to cluster together. Nevertheless, we saw a pretty nice relationship between the rate of change of load force and weight and the rate of change of grip force and coefficient of friction. In fact, the scaling of load force rates to weight could be predicted at a population level. So even though each individual scales slightly differently, their baseline is their intercept is different, there is a relationship in the population, which we can now use as a benchmark. So one of the things that we wanted to understand is what is the relationship between the scaling, which is really your behavior, and how that behavior is generated, that is muscle activity. So what we found was that in control subjects, if they're lifting a light and a heavy object, what really matters is the muscle groups that they are lifting the object with. So for example, if you're lifting by flexing at the shoulder, then you see that what's really different between the light and the heavy objects is the activation of the lifting muscle, that is the anterior deltoid. However, when you look at patients with stroke, you see that there's a lot of co-activation. Multiple muscles are activated. And we wondered if this is related, the co-activation is related to their inability to feel the weight of the objects. So when we had the patients lift with the good hand, the relatively good hand, and then with the affected hand, what we saw was actually that the co-activation decreased in patients with stroke. So this is very interesting and kind of goes along with what Etienne presented earlier, where there was, if you reduce co-activation, you increase perception, sensory perception. Here, we improved sensory perception by enabling the individual to receive the information from the other hand, and we saw that the effect was in reducing muscle coactivation. So now this grasp and lift task actually can assess many aspects of hand function quite comprehensively. So for example, the time taken between touching the object and beginning to exert forces in the vertical direction, or the load forces, is the time necessary to stabilize grip. And we know that in healthy individuals, that's only about 100 milliseconds long. Okay, so that tells you about grasp execution. The scaling of the grip force rates, as I've talked about, tells you about taction, or the ability to use your sensory information to adapt your forces. Load force rate tells you a little bit about how they sense the weight of the object. So it tells you about proprioception. The time taken to decelerate the forces actually tells you about feedback control, okay? And as other folks have talked, Ilana especially, this relationship, this efficiency of grip force at the time of lift, or the grip force to load force ratio, tells you about the efficiency of coordinating these forces, right? Because we know that individuals end up using just the minimum amount of grip force needed. Whereas in a lot of patient populations, we see that they're not able to get to that minimum. They actually, even patients who are motorically impaired, they actually use excessive grip forces in a task like this, okay? So basically, this simple task gives you a lot of comprehensive information about what's happening in the sensory motor system. And in fact, people have shown, Wenzelberger showed way back in 2005, that grasp execution, that is this preload phase duration, which is typically just about 100 milliseconds in healthy individuals, is related to the involvement of a specific area of the internal capsule, that is the pathway through which the corticospinal tract travels. And we know that the greater the involvement of this posterior limb of the internal capsule, this area here between these two lines, the greater the disruption to hand function. And so what they found was that the more posterior the lesion, so closer to this red line, the greater the preload phase duration, right? And what we saw was that with this alternate hand training approach, where you're exploiting the sensory information that is coming in normally into the unaffected hand, you can actually not only improve force scaling, as I showed before, but you can also reduce this preload phase duration, okay? And that has implications for how quickly you might be able to manipulate objects, like, a bottle you want to pick up, or any hand function task. Because clinically, we measure hand function by the time it takes to put pegs down on a pegboard, or manipulate objects, the time taken to manipulate various daily objects. So in fact, what we found was just 4 weeks of this type of alternate hand training also improves their pressure sensitivity, stereognosis, 2-point discrimination, pinch strength, as well as the time on some of these, the Wolf motor function test task, which is, these are hand tasks for a very commonly used functional test battery after stroke. And it's also related to perhaps quality of life. Now, it's one thing to look at a cohort of subjects, but we all know that there's a great deal of intersubject variability, right? And as Ilana mentioned, especially, in patients with stroke, we have so much variability between each individual's sensory and motor disruption as a result of the lesion. So what we were interested in looking at is, how in individual subjects can you actually look at whether they are normal in one aspect and whether this alternate hand training improves or makes their values, are they normal and they become abnormal, or are they abnormal and they become normal, and every combination. And so essentially we find that for some patients they are abnormal with the affected hand to start with, but then after practice with the unaffected hand they become normal. But it's not true in every case. Okay, so so what we really started to think about is that we really need to think about recovery in an individual manner. Because if we want to have precision rehabilitation, we need to be able to provide the right treatment to the right patient, depending on all these various factors, their sensory and motor deficits. So we asked what type of sensory information is critical to recovery of grasp. And we designed a study where we basically either provided tactile, visual, and kinesthetic input, so we didn't block any, or we blocked either the tactile or the visual or the kinesthetic or any combination. Okay, and we asked, how do these inputs contribute to the transfer of information to improve grasping with the affected hand over a single session? So we had two sessions, one where basically the weight of the object was constant and we only had them perform the task with different textures. Okay, where we had 4 different textures, we randomized them, and they performed the task first with the affected hand to see what their behavior was like, and then after using the unaffected hand, and then using the affected hand. And so here's what we saw. We performed a cluster analysis where we were trying to understand which patients responded to which tactile conditions and which grasp variables actually showed an improvement as a result of using the unaffected hand. This was a cohort of 40 stroke patients, and overall we found that 60% of patients were responders, but exactly how they responded was different. Okay, so for example here, if you're only looking at the texture being constant and we're looking at adaptation to weight, we find that a cluster of these patients showed improvement in the preload phase duration, that is, grasp execution. And the big difference between those who responded, which is the cluster, and the rest was the big difference was that the cluster that responded was more impaired motorically. The other variable that responded was deceleration time. So basically, as a result of training with the alternate hand, they now had better feed forward control. They could reduce their deceleration time. When we looked at the texture trials, the texture session, again, we saw that it was the preload phase duration and the deceleration time that responded. But this time, it was the visual and kinesthetic information that actually helped to improve. So I guess for the weight studies, it was the combination of tactile and kinesthetic information from the unaffected hand that was critical. For the texture trials, it was the visual and the kinesthetic information that transferred. So again, because of the individual variability, it's important to understand, were these patients more impaired or less impaired? And what we found was that if they were less impaired they actually showed a greater ability to transfer this information. If they were less visually impaired, also they were better able to transfer the information. So what we did was we then created a grasp kit. So many of these studies are done with complex equipment in a lab setting. Our question was, if we were to provide precision rehabilitation and we needed all of this information, it has to be available to everyone anywhere. So the grasp kit consists of an instrumented object as well as grasping pads with different textures and little weight boxes of different weights that you can fit in there. And we had the opportunity to test this in a DoD-funded study in multiple sclerosis in over 60 patients. Now, at this time, we were not able to do any real-time analysis, so we are currently analyzing this data. And then we decided that we need to really create a more engaging platform for them to, even acquire this data. So what we've done now is we've created an app that enables an individual to enter their information. You can talk to the app and basically do a very quick and easy grip assessment that can inform, what type of therapy technique might work best for a given patient, when and why. And basically what you get is a data that can be easily interpreted by a therapist or a physician, where here you can see that overall the greatest impairment for this patient is in traction. So in other words, they cannot scale their forces to the texture compared to the unaffected side, right? Proprioception is also impaired. So there are two weights. With the unaffected hand, they can scale, but with the affected hand, they cannot scale. Execution or the preload phase duration is extremely prolonged. And in terms of coordination, that means using just the right amount of grip force for a given load. They're not able to do that. They use excessive grip forces. Now, knowing this is important, but let's say you have them practice, you also want to know how well they are progressing. So we created an index that looks at the similarity of the affected hand to the unaffected. Here we're using the unaffected as a benchmark, and it tells you how they're doing in all of these variables, right? So the idea here is that a simple grasp assessment tool can take into account both sensory as well as motor aspects of hand function and facilitate precise assessment, personalized treatment, easy reporting, and guided therapy, potentially at home as well as in the clinic or the hospital. And we hope that, as this is deployed more, we will be able to eventually return patients to flexible hand function. So I'd like to acknowledge many people who've worked on this, as well as my collaborators who are at NYU and several other places, as well as the funding sources. With that, thank you very much for your attention.
Thank you so much, Preeti, for an amazing talk. It's always a great pleasure learning about your work. It was very impressive presentation. So thank you so much for sharing the results. So I have one question, and that's about the transfer of information between the affected and unaffected side, which is amazing. So my question is that do you think that there would be effect of like a perceptual memory? I mean, if you, after doing that task, after doing the task with the unaffected side, if you give them some time and then redo the task, do you expect to see the same change? Or, I mean, does memory play an important role here, or is more a therapeutic with longer term effect?
Yeah, so studies have shown that in healthy individuals, the memory lasts for at least 24 hours. Right? So in patients with stroke, the idea is to initially, when we had the patients do the task with the affected hand, even with repeated practice, they did not scale, right? There wasn't a memory. They couldn't establish a good sensory motor memory like we do in one trial, right? However, when individuals use the unaffected side, then on the very first trial, that there is that memory of having performed well with the unaffected side. But with repeated practice with the affected side, that gets washed out. So this whole idea of alternate hand training is to practice in such a way that every time you practice with the affected hand, it is preceded by practice with the unaffected hand.
I see.
So if you do this often enough, then the idea is that you will establish a sensory motor memory. You're basically creating that association. You're creating that learning, and over time that will become a constant memory, and that will be basically recovery.
That's amazing. Thank you so much for the answer. So I see there's also a question in the chat box asking that any thoughts on providing active sensory feedback for rehabilitation, and what kind of haptic sensory feedback you would use?
Yeah, so basically the object here where you can change the weight and change the texture is haptic sensory information, right? You're providing that from the unaffected side here. So in other talks, you've heard about how you can stretch the skin and you can use vibration. So I think there are other ways to provide that type of sensory information. We haven't specifically studied that. We've been looking at, natural objects, but extracting their properties and putting it in this instrumented grasping object so that we can study how patients adapt.
That's great. And I think maybe the last question would be, again, from the chat, asking you about, I was wondering if you looked into the activity changes of the tactile afferent before and after stroke, with some of the afferent information missing after stroke.
Yeah, so many patients had a great deal of variability in the degree of tactile, proprioceptive, visual, and motor dysfunction, right? Which is why, so actually we have so much data that analyzing it and making full sense of it has been the big challenge. But we clearly see, so in the data that I presented to you, we were looking specifically at, does sensory impairment have a role in transfer? And it seems to have a role, clearly. Those who you needed to have some intact sensory information processing ability. So maybe that meant that your sensory cortices are intact, right? In order to actually use the sensory information from the unaffected side to apply it and to improve the motor performance with the affected side. We have done imaging studies as well, but we don't have that data yet.
Thank you so much, Preeti, for a great talk. There's a lot of positive comments and excitement in the chat also. So I think we can move on to the next section, which will be, we have another invited talk, but we have like 2 minutes. So maybe we can get a very short 2-minute break and then come back at 12:30 Eastern time. Thank you.
Thank you.
Sorry I missed this morning. I would have much preferred to be here. I promise you that.
Oh, thanks for being here now, and don't worry about it. We have everything is being recorded and it's broadcasted on YouTube, so we have that YouTube link. But yeah, it's great to have you here. Thanks for joining us.
Thanks for having me.
Yeah, thank you for joining us. Thank you. It's a great pleasure to have you.
So we have, I think, 1 minute and then we start.
Should I share my screen?
Yeah, perhaps, yeah, that's a great idea. What if you share the screen and then, so we can start right at 12:30.
Oops, wrong screen.
Yeah, looks great.
But that was the wrong screen, wasn't it? Let's see, let's try this one. Nope. All right, let's try it again.
I think it was the right screen. I think it was a correct one.
The first one was the correct one?
I think the second one also, we saw the same screen.
Yes.
This one, no, this one you're showing your, yeah. So now we are seeing the presenter view, but before it was, yeah, we're seeing.
All right, hold on a second. Let me try this again. Like I'm a new, like I haven't done this 1,000 times before. All right, let's.
It happens all the time. Yeah.
Yeah. The first one actually was a full screen.
Was it? Is this right?
Yeah.
Yes,
Yeah, this is
yes.
great.
Okay, cool.
Perfect.
All right.
Okay. So let's resume the workshop. So hello everyone again. It's my great pleasure to introduce Suleiman Benzmaya from University of Chicago, and the topic of his talk is toward unraveling the neural basis of stenosis.
Thank you. So let me just tell you a little bit about what we do in my lab, just very briefly to sort of frame the rest of the talk. So what really gets me out of bed in the morning falls under the rubric of neural coding. And, I'll use a touch example, but the idea is, when you're interacting with an object, there's this pattern of skin deformation, which is what this squiggly line is. And that leads, and there's receptors in your skin. I mean, I know all of you know this, but there's receptors in your skin that transduce these patterns of skin deformations into patterns of neural activation in the nerve. That's what these little tick marks are, is action potentials of a bunch of different nerve fibers. And then this neural activity propagates up the arm, and then along the neuraxis, first in the cuneate nucleus, then in the thalamus, and then through successive stages of processing in cortex, ultimately giving rise to a perception of this object. And when you grasp an object in your hand, you have information about its size, its shape, its texture. If it's moving across the skin, you have information about that too. And somehow all this information that is available to you about this object is contained in these patterns of neural activation. And so what we spend all our time doing, or some of our time doing at least, is trying to figure out what aspects of these neural patterns at each stage of processing in the nerve and in every subsequent stage, what aspect of this neural activation contains the information about texture, about shape, about size, etc. And we're not just interested in the information content of this neural activity, of these patterns of neural activity. By the way, most of the work that I do and that I'm going to show is in rhesus macaques, which are basically the most human-like things you can stick electrodes in. And so we're interested not only in the information that is contained in these patterns of neural activation about objects grasped in the hand, but also about the relationship between these patterns of neural activation and perception, and the perception and the resulting perceptual experience. So for instance, if you give me a pattern of neural activation, and we develop these pretty quantitative models. So if you give me a pattern of neural activation, like in the nerve, I can tell you what the texture is, or whether it's moving, or if there's some kind of shape there. And I can, if you give me two patterns of neural activation, I can tell you, well, this one is going to give rise to a rougher sensory experience than that one, or maybe even twice as rough, kind of quantitatively predict not just what the stimulus was, but also what the resulting sensory experience was. Here my gum here. Okay. So what I'm going to talk about today is what I think of as one of the most interesting questions in somatosensation, and that is the neural basis of stereognosis. So so as probably most of you already know, stereognosis is the perception, when you grasp an object in your hand, you have this very vivid three-dimensional percept of this object, right? And what we want to understand, how is it that the nervous system gives rise to this? How does the nervous system do this? And so just first of all, we need to understand, what does this imply? What are the parts of stereognosis? So one part is the fact that at every contact point with the object, the skin is making contact with it, and you have the cutaneous signals give you information about the local contours of that object, right? So here, for instance, this is a phone, and like all the fingers here are making contact with a specific edge of this phone. So, and each finger tells you, oh, there's an edge there, and this is the orientation of this edge. And then the thumb is touching the other edge, right? So then signals the presence of an edge there. The palm is maybe touching part of the back of the phone, so it tells you something about the surface there. But ultimately, and what's really fascinating to me is that these signals from the skin have to be interpreted these signals from the skin at each point of contact have to be interpreted in the context of where these points of contact are relative to one another in three-dimensional space. And that information is conveyed by a completely different sensory system with, that instead of coming from the skin comes from the muscles and the tendons. And that is proprioception. That tells you what the shape of the hand is, right? And from the shape of the hand, you can then infer where are these contact points relative to one another. And, and all the work that, the overwhelming majority of the work that has been done trying to understand the neural basis of somatic sensation has studied the cutaneous signals in isolation or the proprioceptive signals in isolation, but have not really understood how these two kind of streams of information are integrated in general, and more specifically, how they're integrated to convey the kinds of information that is necessary to support our ability to haptically perceive the three-dimensional structure of objects. And we know, for example, that everything is unimodal, in the nerve, in the cuneate nucleus, in the thalamus, in areas and in the early stages of cortical processing. And that only in Brodmann's area 2, which is the third cortical stage of processing, is this information integrated, and then and of course beyond. So what we're interested in is how is tactile information integrated with proprioceptive information, and how does this integration process give rise to stereognosis? I just want to point out the hand, I mean the skin in general, but especially the hand, is the only deformable sensory sheet in the body, right? And somehow the brain has to solve this problem for the hand that it doesn't, and for the skin in general, that it doesn't have to solve for any of the other sensory modalities. And that to me is, from a neuroscience standpoint, really cool and interesting. Okay, so what I'm going to do now is I'm going to try to quickly tell you what we know, that is relevant to this conversation, right? And the first aspect is, well, what does the skin tell you about an object? And of course, there's a ton of work that has been done, but I'm going to give you a very broad overview of sort of the take-home message of some of the work that's been done on this topic. So, when you grasp an object, at every point of contact, you know something about the local geometry of the object. How does the nervous system encode that, right? Well, this is a big body of work that was really, kind of a lot of it was pioneered by my postdoctoral advisor, Ken Johnson at Johns Hopkins University. And what they showed by recording the responses of nerve fibers in the digits of macaques to a bunch of different spatial patterns, is that the spatial pattern of activity in one of the populations of nerve fibers that innervates the skin, there's really 3 to 4 main ones, but that one of them, the slowly adapting type 1 or SA1 fibers here, is shown here on the top row. Really, if you reconstruct the population activity across this entire population of afferents, and you look at the spatial layout of the activation, you see that it recapitulates the stimulus, right? And you know what the stimulus is here just by looking at the neural activity, hopefully, right? Where you can see that these are embossed letters scanned across the fingertip. If you I don't want to go into the methodological details because they're not relevant, but the important thing is, if you could reconstruct the entire population response of slowly adapting type 1 afferents, it would just look like the stimulus, right? And this is a kind of like in vision, right? If you look at an A, you have an A pattern of activation in the retina. Well, if you press your finger on an A, you get an A pattern of activation in slowly adapting type 1 afferents, and to some degree in RA afferents here shown in the middle. And then PC afferents don't really have any kind of spatial activation pattern. So in the nerve, you have this very isomorphic image. It's like a neural image of whatever it is you're touching. And then when you look down in the brain, so what we did, this is a study I did when I was still at Hopkins, where we indented a bunch of bars into the skin of a macaque while recording from somatosensory cortex. And what you find is there's a large population of neurons in the cortex that are feature detectors, right? And so this is just an example for an oriented edge, because the world that we live in has a lot of edges in it, particularly in artificial objects, right? So if you scan if you indent an edge into the skin and record the neural activity evoked, so here's the edges here, and here's the neural activity evoked by each of these edges, you can see that and each tick mark corresponds to an action potential. So this is like a neural signal that this neuron emits. You can see that this neuron barely responds to edges that are aligned with the long axis of the finger, and responds very strongly to the same edge that is, when its orientation is perpendicular to the axis of the finger. So you can plot the strength of the response of this neuron as a function of the orientation, and you can see this really nice orientation tuning where this neuron is a feature detector looking for a specific feature, in this case, a horizontal edge. And this is just an example. There's another neuron that's going to prefer a vertical edge, another neuron that's going to prefer some kind of diagonal edge, and another neuron that doesn't like edges that much, but likes, for instance, specific patterns of dots, indented into the skin. And so you can think of these neurons as little geometric feature detectors that are going to respond to specific patterns of spatial deformation of the skin, right? And what's really cool about this, from a neuroscientific standpoint, is that that's how the visual system works, right? The visual system has this isomorphic image of the visual scene in the retina, and then as you ascend the visual hierarchy, you have these little spatial feature detectors that sort of detect increasingly complex features. And what we and others have shown is that the same is true in the somatosensory system. So so this is just to show you that so this is an orientation index, the cumulative distribution of an orientation selectivity index. There's no orientation selectivity in the nerve. And if you look in the cunea, so this is hot off the press, no one has seen these data except for people in my lab and you now, is that in the cuneate nucleus, there's also some orientation selectivity. So it's not something that happens magically in cortex. This is something that has already started happening in the brainstem, the first stage of processing in the somatosensory neuraxis. And then there's even stronger orientation selectivity in cortex. So this is a process of extracting geometrical features about objects from cutaneous signals that we and others have been documenting. So that's how you get information about the local features. So that's the take-home message. Let me just move on. But of course, the second half of that, the second half of stereognosis is understanding how does the brain track the hand. The hand is a complex thing. There's 30 degrees of freedom of movement of the hand. It is a very versatile and complex effector, as has been said in the previous talk. So how does the brain track that, the conformation of the hand? So to address that question, we have a completely separate line of inquiry, which consists in having animals reach and grasp, or actually in this case, just grasp a bunch of different objects, right? So the objects are brought to the animal with a robot. These are the objects that we use, and we try to have a bunch of different shapes and sizes to force the animal to do different things with its hands to grasp the object. And then for this particular study, we use a Vicon system, which is like a sort of a motion capture system that basically tracks the position of IR markers on the monkey, which is a real pain in the neck. I'll just kind of preview something I'm going to say later. It's a pain in the neck because you know what the animals do? They want to chew the IR markers off, and you spend 2 months training the animal not to chew the markers off. Anyways, that's a problem that's been solved, as I will show you later. So as the animal is grasping these various objects, we're recording from sensory motor cortex. I'm just going to talk about the somatosensory stuff today, but we use a variety of different technologies, but the most successful technology for this was a semi-chronic array where it's like 100 electrodes placed over sensory motor cortex, and we can drive each electrode independently, so which allows us to move the electrodes through the cortex, which is good because some structures, like for instance, Brodmann's areas 1 and 2 are at the surface, and other structures like Brodmann's areas 3A and 3B are in the sulcus. And this technology allows us to actually chronically access both. Okay, and we're going to be recording for the purposes of this talk, I'm going to be talking about areas 3A and 2. Those are going to be the areas of interest. Forgot it. So this is what the data look like. So here we have an animal grasping an object, and then we reconstruct its hand movements shown on the right. And then the sound is the response of an area of a neuron in Broca's area 3A. That's really loud. I hope it's not as loud for you guys as it is for me. Okay, so this is just to show you that we can then reconstruct the hand kinematics, and each of these traces corresponds to the joint angle of each of 3 joints to each of 35 objects. And you can see that these joint movements or these joint trajectories vary on an object to object basis, which is important. The animal kept doing the same thing over and over again, that we couldn't really gather or infer anything about the neural representations. In fact, the joint movements are different enough that before contact, we can guess which of the 35 objects the animal is about to grasp, because it precisely pre-shapes its hand to the object. And we've actually written extensively about that. But that's good, because that means that we have 35 different hand trajectories that are being elicited in this task. And so the question is, how does the brain, we're recording from these neurons in sensory motor cortex, what turns these neurons on? What are they tracking? What are individual neurons tracking? So the way we address this, we address this in 2 ways, but I'll just show you one of them. Is by, so here, these squiggly lines here are all 35 joint angles, or the 30 joint angles that we're actually tracking, at least a subset of them. And what we do is we try to find, using the generalized linear model, which linear combination of these joint angles pass through threshold in nonlinearity best predicts the response of this neuron. And anyways, basically what we're trying to find is which aspects of the hand movements are driving a neuron's behavior, right? And these models do pretty well, surprisingly well, given the complexity of the hand. So the color traces there are the predicted responses the measured responses of a given neuron during the grasp of 4 different objects. And then the black traces are the reconstructed responses, or the predicted responses based on the GLM. And you can see that those capture really the core structure of the response. Okay, so then the interesting thing here is, okay, so now that we have a good model of what turns each neuron on, let's look at what turns each of these neurons on, right? And what we find, for example, you might think in area 3A, it's the very first stage of processing of proprioceptive information. Maybe these guys are just tracking a single joint, right? So there's a thumb neuron, and then there's an index neuron, and then there's a whatever. It's like the basic building blocks of what the hand is doing, right? In fact, that's not the case. If you look at neurons, even in area 3A, so that again, the very first stage of proprioceptive processing in somatosensory cortex, you find that these neurons actually encode information across multiple joints, on average 8. And these joints are like distributed over the entire hand. So a joint might be turned on by the wrist, the thumb, and the pinky. It just seems really haphazard. There doesn't seem to be any structure, but the important thing is they seem to be really encoding information that is distributed over the entire hand and not restricted to a single joint or even a single finger. The other thing that we found is that you might in the arm, if you look at proprioceptive sensory motor representations of the arm in general, in fact, they respond primarily to movement. So like you have these huge phasic responses when the arm is moving, and then the responses dwindle to nearly nothing when the arm is still. And these neurons, the interpretation is that these neurons really respond or encode the velocity of the movement, not the posture, right? And so that is, one of the standard findings in every single part of sensory motor cortex for proximal limb representations. What we found for the hand, though, is that in fact, the hand neurons don't respond preferentially during movement, and in fact, seem to be tracking the time-varying angle of the hand, right? And that seems very well suited for stereognosis, because you can read out, and we've shown that you can read out, at any given time, the shape of the hand from the pattern of neural activation in S1 directly, right? So that's the proprioceptive take homes. But I promised you, and I'm running out of time, so I'm going to try to rush through this quickly. But I promised you we were talking about stereognosis. So what gives? How can we now try to understand how these cutaneous signals and these proprioceptive signals are integrated? And I think the main challenge has been, so in the first stuff, in all the stuff that's been done with touch, the vast majority of the stuff that's been done with touch, you have the still hand and you're presenting stimuli. So that just takes out proprioception altogether. In the proprioceptive studies, we only study up right before the animal has made contact with the object, because the instant the animal makes contact with the object, there's all kinds of forces being exerted on the object that are going to be reflected in the neural responses, but that we're not measuring, right? So we have created, but what we do, just from looking at the data that we've already collected, maybe I should stop. I'm going to stop after this slide, and I'll answer questions later if somebody's interested. But from the data that we've collected, here's what I can tell you, right? We can record the neural activity evoked in these various areas, and then we can see how that activity is object dependent, right? And so and as I said, as the animal pre-shapes to grasp an object, the shape of the hand is going to be reflected in the neural responses, and therefore we can actually decode what the object is before contact, just from the pattern of neural activity evoked in the brain. And that's what this this trace here shows, right? Let's just focus on area 3A. It's just tracking the movements of the hand. And because the hand pre-shapes to the object, these neurons reflect what the hand is doing, and therefore we can classify what the object is. So this is proportion classification of what the object is based on these patterns of neural activity. And we can do it based on activation in 3A, and less so in these other, in area 1, which is purely tactile. You don't expect to do very well because there's no contact with the object. And in area 2, there's some proprioceptive information there too. So that's why you're able to classify it. But here's the interesting and relevant thing. The instant you make contact with the object, suddenly, now you have these, this is where stereognosis kicks in. You have these cutaneous and proprioceptive information encoded in area 2, and your ability to classify the objects improves, right? Consistent with this, the idea that in area 2, you have the information that you need to achieve stereognosis, and not so much in area 3A, right? Because in area 3A, even when you make contact with the object, your ability to classify the object based on these neural responses is not much better than it was before contact. Anyways, so I don't have time to get into it, but I'm just going to tease you by telling you that we have now developed a rig that allows us to measure all the hand movements of first of all, present an object anywhere in 3-dimensional space that we want, and change the shape and size of this object as we want. The object is fully sensorized, and then we use basically computer vision, this algorithm called Deep Lab Cut that we've adapted specifically for the hand, so we don't need the IR markers anymore to track hand movements. So we know what the forces are on the object. We can change the object, and we can track the motion of the hand or the posture of the hand. We can put all that in a physics engine to reconstruct which parts of the hand produce which forces. That's what this shows here. And now we record from the entire neural axis. So now we're in a position to see during natural prehensile movements how information about objects is encoded at each stage of processing. We have all the data for the first time that we need to really understand how tactile and cutaneous and proprioceptive information is integrated to give rise to stereognosis. So maybe next time I give a talk at this meeting, I'll have better answers for you. This is the lab. These are my funding sources, and thanks for your time.
Thank you so much. It was an impressive presentation and a lot of great results. So thanks for sharing with us. So so there's a question, I think, in the chat. Mohammed said, mind-blowing talk. I wonder if we can determine those physical properties, texture with stiffness using non-invasive brain imaging, and how to relate neural activity with cognitive functions, perception and stiffness or texture.
That's a great question. It really depends on what the fundamental questions you're interested in. I think one of, I did my PhD in psychology, right, where we're just doing all our work with humans. And there are certain questions that you can completely address using psychophysics and non-invasive techniques, right? But the kinds of questions that I'm interested in understanding, right? Like, for instance, you can use non-invasive approaches to tease out which are the unimodal areas and where does this integration happen. Those are the kinds of things that you can address. But if you want to understand the information flow, the nature of the representation at each stage of processing, at the level that we, which is what we are interested in, right? Ultimately, I'm a sensory neuroscientist and I love somatosensation, right? But the thing that gets me out of bed is that I feel like these questions allow us to understand how nervous systems give rise to flexible intelligent behavior. I mean, sensory processing is, is staggering in its flexibility and intelligence, and completely, smashes any kind of artificial device ever devised, right? So there's some intelligence built into the sensory processing, and we're interested in understanding that at a very mechanistic level. And I think that's hard to do. I mean, in my experience, it's hard to do non-invasively. What was the second part of the question?
How to relate neural activity with cognitive function, like the perception and stiffness and texture with cognitive function.
Right. So, one of the things that we do, which I didn't talk about at all here, but is that, we try to predict perceptual experiences, right? And, at every stage of processing, all the information that is consciously available to you is present in that pattern of neural activation. And so we build these very precise models of, how, what is the relationship between the perceptual experience measured in psychophysical experiments and these patterns of neural activity. And we're very successful in doing that, even though it's cross species. We're getting the neural activity from monkeys and then the perceptual experience from humans, sometimes from monkeys too. But I'll say one thing about cognitive. The cognitive stuff is not something I've spent a lot of time doing. But here's one cool thing that I can tell you about that, is that we just started, this is unpublished data, it's not even on the archive yet. We just started probing as secondary somatosensory cortex. And we're not the first. There's stuff that's been shown like this before. But what's really interesting about secondary somatosensory cortex, in contrast to every other structure that I've talked about today, is that there are cognitive variables, right? So the task was, we have animals doing a texture discrimination task. And so there's a lot of texture information there, obviously, right? But there's also information about, the animal is presented with two textures and has to say if the second is the same or different. And there's neurons that will just tell you if the second texture was the same or different. And then there's other neurons that will tell you whether it was so one population of neurons is predictive of the animal's behavior, and the other population of neurons just tells you, oh, there was a change, and so there's all kinds of more cognitive sort of task relevant variables in S2, but that's about as far as I can tell. That's probably better done in humans at this point.
Thank you so much. So I think I have one question, and then we can move to the next speaker. And that is, I'm curious to hear your opinion about this concept of sensory synergy. I mean, in motor control, we often hear about muscle synergy, and now you're talking about in your talk, you talk about how proprioception and tactile is being perceived by central nervous system. So, is there any study related, or are you interested in how you can comment on the concept of sensory synergy? Is it like how the brain functions in processing this multidimensional data? Do you think that there would be a dimensionality reduction through this concept of synergy?
I am so glad that you asked that question, and I'm sure I'm going to piss off a lot of people with my answer, but I am not a big believer in synergies, and I'll tell you what it is. Actually, we just published a paper in Nature Communications about a year ago on this, right? If, the idea of motor synergies or muscle synergies is based on, you look at the kinematics, or you look at your muscle activations, you do a principal components analysis, and then you see, oh yeah, like 6 or 7 dimensions PCs can account for X amount of the variance, whatever, right? But who cares about variance explained, right? I mean, the wrist moves a lot more than the DIP, but does that make the wrist more important? Actually, it probably is. In this particular case, it was a bad example. But Now, if you look at all these other PCs, you know, the synergistic kind of view says that all these other PCs are just noise, they're meaningless. But what we've shown is, in fact, they're not meaningless. In fact, these other PCs are very much under volitional control. They just happen to move the finger a little bit less, right? And you can just remove 90%, or you can take all the synergies out and still know which object is about to be grasped, right? And you know, and this the idea of synergies came from a time, I think it's before my time, but where, you know, we thought maybe the brain needs to simplify the motor output problem. But actually now that, you know, subspaces and dimensionality is now in the forefront of, I think, a lot of what, you know, neuroscientists think about. You know, the idea that the brain would need to whittle this down to a few dimensions, to even 10 dimensions, is kind of silly, because when you think about sensory processing happens on, you know, these much larger, you know, orders of magnitude more dimensions effortlessly, right? So why would we whittle down the motor? So that's my answer. I don't believe in motor synergies. So now you can guess that I believe in even less in sensory synergies, right? And so in fact, what I was hoping to be able to do today is show you a model that we're starting to work on about what computationally it is involved in stereognosis. And what we show, I'm going to tell you what the model shows. I don't have time. It's like a machine learning type model. But what it shows is, if you want to do stereognosis, you have to combine tactile and proprioceptive information before any kind of nonlinear processing happens. If you just always keep them segregated, you cannot do stereognosis. You cannot tell objects apart. The second interesting thing is, in order to do it well, you need to integrate information across fingers. If you force your model to only have access to one finger, even proprioceptive and cutaneous information from one finger at a time, you also can't do stereognosis. So we're thinking about it, but not from a synergistic standpoint.
Thank you.
And
this
I
is
apologize to all of you.
It's great talk and answer. Thank you so much for impressive presentation. So we can go to the next topic. We can move on to the next presenter, who's actually co-organizer of the workshop, and my great colleague, Mohammed Eid. And the topic of Mohammed's talk is toward neural encoding of haptic experience. And Mohammed, the stage is yours. You are muted, but we do see your screen, yes. I can try to unmute.
Yeah.
Okay.
Yeah. Thank you very much, Farouk, for the introduction. And hello, everyone. My name is Mohammed Eid. I'm an assistant professor of electrical and computer engineering at New York University here in Abu Dhabi. And I'm going to take you briefly about our experience for the last few years looking into neurohaptics from the perspective of trying to study and characterize the human haptic experience. And I also wanted to mention that my research group also develops research in effective haptics and in emerging haptic interfaces, in particular mid-air tactile stimulation using ultrasound. So I'll start by motivating the work that we've done, and then I will present a very high level overview of the approach that we use, which combines neuroscience with artificial intelligence to try to understand the human haptic experience. And then I will take you through a couple of examples. The first one is trying to understand how haptic delay, in particular force feedback delay, how it's encoded in the brain. And then the second is how to infer the vibration intensity from neural activities, again, in the brain. All of these are based on EEG recordings, and then I'll wrap up at the end with some conclusions and maybe providing some perspectives for future work. So, Sliman talked about how you can characterize and you can understand physical properties using neural correlates, and I'm very interested in this from a kind of quality of experience point of view, where we find this very challenging. I mean, trying to describe how the user feels about or how they can describe their touch experience is very challenging. And the way the community addresses this is using self-reporting, where we just provide participants with a bunch of questions in a questionnaire and try to capture their experience. Or we sometimes use physiological measures like ECG, like respiration, skin conductance, etc. Or sometimes we use some performance matrices, which involves, for example, the task completion time, maybe the accuracy of performing a task, etc. So all of these combined provide great ways of capturing the human experience, but there is also an interesting emerging field in cognitive quality of experience, which is basically trying to tap into the brain and try to understand the mental state of a particular haptic experience. And for that, you could use different kind of brain imaging techniques such as fMRI, EEG, FNIRS, or MEG. We are particularly interested in EEG because it's low cost, because it's also electronics devices friendly, so you can use it with electronic devices, in particular the haptic interfaces, and of course because it has a high temporal resolution. Of course, the applications are many, mostly in the neural rehabilitation and physical therapy, particularly for sensory motor rehabilitation. It also would inform research in cognitive human-computer interaction, and in particular brain-computer interaction. And of course, it has other applications such as training, education, and entertainment. So here is a brief overview of how we are doing this. So imagine we have a human subject interacting with a haptic interface, whether this could be force feedback or vibrotactile interaction. We continuously record EEG data, which captures the electric activity of the brain using this cap of electrodes that are attached to the scalp. Excuse me. And then we use, because we know EEG data is very noisy, excuse me. So we use data pre-processing. For example, we amplify the signal, we filter it, we perform kind of artifact detection and removal. And then we have denoised EEG data, which is fed into a feature analysis component that tries to extract some higher level knowledge about those activities and try to make sense out of them, and then feed these features into a quality of experience model, which you could imagine it would be a machine learning model that would get those features and try to understand what the user is experiencing. And this model can also be either complemented with other measures like self-reporting, physiological, or performance measures, or it can be also cross-validated with those. And the model would just give you what the user is experiencing. For example, what is the intensity of vibration that the user is feeling, or what is the force magnitude in a force feedback interaction paradigm, or for example, if there is any haptic delay in the interaction. So zooming into EEG data processing, there are three phases that we work with. First, after collecting and recording the EEG data, we do filtration, which sometimes we do low, high pass, band pass, depending on what we're looking for. We also use artifact removals, because these are activities that come usually from eye blinking, from muscle activities, movements in general. And then we also do epoching, which is basically trying to extract a particular time window from the continuous EEG data, which is usually time locked to a particular event, such as, for example, a haptic stimulation. So once we have all of this information, then we start analyzing this data. For example, we extract ERP, event-related potential, which is simply the change in the activity in microvolts over time. We also look into frequency domain analysis like power spectral density across different frequency bands that are known in the EEG community, like the delta, theta, alpha, beta, and gamma frequency bands. We also look into time frequency analysis, which we look into the into the powers of these frequency bands over time. We also can look into functional connectivity to understand the spatial and temporal relationships between different regions or even different electrodes. And finally, in the feature analysis, we look into techniques like localization to find out a very specific area in the brain that has the most prominent activation. We could do some averaging to increase the signal to noise ratio. We sometimes also use statistical analysis or machine learning, particularly explainable machine learning, to better understand prominent features for a particular haptic experience. Now, once we come to the second part of this, which is trying to predict what kind of haptic experience the user is having. Here we look into, first of all, identifying what features are more prominent, which regions, and eventually which channels to focus on. And then we get into the kind of the classical machine learning work, which is labeling all the data, and sometimes we use data augmentation to enhance the data, the data set size, and then we split the data into training, validation, and testing. And finally, once this is all done, then we could build a machine learning model, which could either provide a classification for the problem, for example, whether there is a tactile feedback or not, whether there is a haptic delay or not, whether there is force feedback, for example, or not, or we could provide a regression model, which provides more of a continuous output in the form of what is the exact value of the haptic delay that the user is experiencing, or what is the exact value of the vibration intensity that the user is particularly experiencing. We could combine these models in a majority vote model, or use explainable machine learning again here to better understand what the model is using for the classification or the regression. So let me take you through the first example, where this is coming from telehaptic research, where when we do experiments, we always face the issue with having haptic delays. These are unavoidable in a real computer network. And the question here is, can we, using the EEG data, can we determine when the user is experiencing haptic delay? And to do that, we actually created a task that involves holding a racket and then kicking a ball. And then there are two scenarios: one, when the ball falls off and then it passively hits the racket, so the user would not need to move their hand, or we call this the passive task, and then the active task is when the user actively moves the racket to hit the ball. And in both scenarios, some of the trials have no haptic delay, but some others have 220 milliseconds haptic delay. And we wanted to study what kind of EEG activities that are created in response to this haptic delay. So here is the task very briefly. So there is the resting period, and then there is the task, and then there is some trials have the haptic delay or some others don't. Now, in terms of the electrodes and frequency bands and time windows that we decided to go for, first we decided to go with the P200 component of the event-related potential waveform, and in particular to the FCZ electrode that you can see here in the middle. And this electrode is very well known for sensory attention. And for the time window, we decided to explore 140 to 280 milliseconds, because this is what's known in the literature for this P200 component to show up. Then in terms of frequency domain analysis, we decided to focus on theta power in the mid-frontal cortex. And the reason why is because it's well reported in the literature for multisensory attention and conflict detection and resolution. So the first thing we noticed is that there was, with the frequency domain analysis, we found that there is a beta rebound that is specific to the delay conditions for passive and active tasks. And in order to visualize this better, we could see here in these figures E and F that the condition with haptic delay had a significantly higher beta rebound than the condition with no haptic delay. And that was true also for the active task. So it seems like the beta rebound is giving us some useful information about whether there is haptic delay in the interaction or not. Then next we looked into theta frequency band, which is in the range 3 to 8 hertz. And we found that there has been significant activation in the middle frontal cortex here that is only shown up in the delay condition compared to the no haptic delay condition. And that was true also for both passive and active tasks. Now, if we plot this in a time frequency space, then we can get these two graphs, and you can see here clearly that the power for the theta PSD oscillation is significantly higher for the delay condition versus the no delay condition, and that was significant for about 200 milliseconds. Likewise, for the active task, there was also statistically significant differences in the peak and in the peak of the theta oscillation. So we think that this could also encode that delay information, haptic delay information. So the other thing we looked at is ERB waveform, in particular the P200, and we found that for the passive task, there was a significant increase in the peak of P200 compared to the no delay condition. That was only true for the passive task. However, in the active task, we did not find any significant differences. We found the P200, but there was no significant differences between the delay and no delay conditions. The other thing we wanted to see is whether there is any learning effect that the users have experienced. And this was reported in the form of plotting the P200 component for the first 20% of the trials versus the last 20% of the trials. And we found that for the no delay condition, it seems like the amplitude of the P200 has been significantly attenuated, and this is kind of predictability of the sensory input. However, in the delay condition, because the participants could not predict when the haptic delay was introduced, so the P200 was still sizable and significant, and there was no significant differences in the amplitude of the P200 component. The second part, once we kind of understood those features, the second part is to try to use those and understand how we can build a machine learning model that could classify and provide us with the information whether there has been a haptic delay in the user experience or not. And the way we did this is by combining all these features. We had 60 channels for 100 milliseconds and for 50 trials. So we just flattened this into one-dimensional data, and then we tried to extract the most prominent features. And we found indeed that these electrodes that you can see highlighted here are the most prominent to provide the classification. So we experimented with classical machine learning like SVM, LGBM, etc. And we also experimented with deep learning, in particular with CNN, and this is the architecture for the CNN model that we used. And then these are some of the results. So we found that we could actually classify the EEG data, and this is single trial EEG data based classification. We could reach up to 83.2%. And this is only based on ERP. When we combine frequency domain features, I think we could also improve this further. The second part is what Haneen will be talking about on Wednesday for her talk. And this is about a classification of haptic task. And it's interesting always to learn whether the user is involved in active or passive task. And we used EEG, single trial EEG data to classify and understand whether the user is performing an active or passive task. So I'll take you very quickly through this. So we use the CNN model and a Lime explainer, which is a technique that is used in explainable machine learning to try to understand or to provide some interpretable features that the human can understand and will make sense to the problem domain. And in this case, we use this CNN classifier. And this is very briefly, I'm going very quickly through this just to allow some time for the second example. And then here, this is the Lime explainer, which basically tries to provide some explanation to how the model is predicting whether there is haptic delay or not. And we could see here clearly that using 4 or even 6 electrodes provides significantly improved percentages for the classification of passive and active task. And we could also see here on the figure on the right side that the training loss is significantly decreasing, which means that the model is actually learning while using 4 or 6 electrodes compared to just 1 electrode. If we look into the explainability results, we found that this is basically what the Lime algorithm provides, and it shows that there is a synchronization in the delta and in the theta bands, which is basically is also confirmed through our previous neurological findings. And then for the active task, we found that there is a strong desynchronization, which is concentrated in the alpha and the theta frequency bands. And these were the most prominent features for the classification. Now, the second part is when we try to encode vibration intensity, and this is inspired by the difficulty that humans have to estimate the intensity of vibration. We used 3 levels of vibration: no vibration, low intensity, and high intensity vibration. We looked into ERP, alpha and beta frequency bands. And this is the experimental setup where the vibration motor was attached to the finger using double-sided tape. And we measured the exact intensity of vibration using a vibrometer, and the frequencies were in 200 to 2040 hertz. The first thing I wanted to highlight is that it was interesting that the self-reporting showed that for no vibration, obviously more than 99% of participants could clearly tell that there is no vibration. For low intensity vibration, also the majority of participants, there was less than 1% who felt that this is like a strong vibration. However, for the high intensity vibration, there was more split findings where some participants reported that these were weak vibrations. So the first thing we wanted to do is to look into alpha event-related desynchronization, and these are simply the low power, let's say, attenuations of the alpha activity. And we found that there was significant differences between the 3 levels of vibration intensity, where the high intensity vibration had a stronger and a prolonged desynchronization. Then we also looked into beta event-related desynchronization, and we found that indeed there was also significant differences in the peak of the ERD and in the rebound, but these were not significant across all the 3 groups or the 3 conditions. Then we also looked into event-related potential, ERP, and in particular, we looked at P200 for sensory correlates, and we looked into P300 for cognitive correlates, and we found some significant differences, but they were unable to encode the vibration intensity. So we are currently looking into building a regression model where we're trying to extract the intensity of vibration from single trial EEG data and try to use this in a real-time application where we could apply different kind of vibration intensities and then extract that information directly from EEG data. So I also wanted to mention that there are some challenges, some limitations in this work, and one of them is how do we bridge sensory representations to higher order cognition? So there are so many other factors that could influence people's experience with haptics, and it's not easy to let's say show a one-to-one relationship. The other thing is the quality of the EEG data. We always have problems, particularly if we use kinesthetic force feedback, then there's always movements, and this creates problem for the EEG system. And also using wet electrodes renders this somehow unpractical, and this is where we're looking currently into using dry electrodes. Just to summarize the findings here, we're been looking into how do we characterize haptic experience using neuroscience knowledge and machine learning, combining these together. We also want to explore other physical properties like texture, thermal stimulation, etc. We also wanted to look into interbrain synchrony using hyperscanning so that we can understand how touch information is encoded, not only by looking at one brain, but maybe by looking at two communicating brains. And of course, we want to look into potential applications to that. So this is a list of some of our publications related to this field. And finally, I would like to acknowledge these great researchers. Without them, none of this would have happened. Haneen, Wanju, Ken, Hassan, Jorgis, and Van. And with that, I'd like to thank you for your attention, and I would love to take any of your questions. Thank you very much.
Thank you so much, Mohammed. It was a very impressive talk and great results that you share. So thank you so much for that. So there is a question in the chat box asking, what made you choose the specific delay of 220 milliseconds, and wouldn't this create some temporal expectancy for the subjects?
Yeah, this is a great question. And the reason why we wanted to use this 220 milliseconds is because we wanted to have a haptic delay that is clearly perceivable, because we wanted to understand whether there are neural correlates associated with haptic delay. Now, in a follow-up study that we're still processing the data, what we did, we provided a large number of, or let's say more than just two delay conditions, no delay and clear delays. So we tried to provide more, let's say, more spectrum of different delays. And we're trying to understand what are some thresholds that, that will have no significant neural effect. So in other words, what would be the minimum delay at which there will be no significant brain activities to detect haptic delay? And that would be really interesting, because the community with haptic, with delay in general has been very broad and very sometimes even conflicting. Some researchers report different kind of delays for different haptic interactions. So we think that maybe capturing this threshold through neural activities could be more quantitative and objective.
That's great. Thank you so much. And so there's another question asking you, would you elaborate more on the finding that clearly differentiate between active and passive neural activity?
Sure. I actually thought not to provide a lot of details because Haneen will be presenting this in one of the oral sessions next week on Wednesday. She also has an office hour, so feel free to join her and talk to her about this in more details. But what I can say here is that we had already the data set that we collected for this passive and active tasks for haptic delay. And we decided to see, because this is also interesting for us to understand whether the user is engaged in passive or active task. And we could actually successfully classify the data at a very high rate, whether the user is engaged in passive or active haptic interaction.
Okay, great. And I actually have one question. So in the experiment that you conducted, the delay was only for the haptic, or the vision was also delayed?
Yeah, so we wanted to focus on the haptic delay only. And this is also driven by what is common in the telehaptic systems, where usually the haptic media is delayed and not the visual media. So this is why we decided to do that. And this is the 220 milliseconds was also supported by a pilot study where we confirmed that more than 95% of participants could actually clearly perceive it as a haptic delay.
That's
but of
great.
course, it's a valid question to see whether, I mean, theoretically, whether the haptic stimulus leads or maybe the visual stimulus is delayed further, or so all of this can be studied. But from a practical point of view, what we know is that it's the haptic medium or the haptic media that will always be delayed.
This is great. Yeah, thank you so much. It's impressive, and I really enjoyed the talk. I think there is another question, and maybe we can call it the last question. Could the So the question is about the variability between subjects in your data, and I think the relationship to age, gender, or other parameters.
Yeah, definitely. I mean, there is a lot of things that we could do with this data. And it's interesting that we collected this data some time ago, but since the pandemic, when we were not allowed to go to the lab and collect EEG data, so we started looking at the data set and we said, okay, let's think about what we can do with this data. And this is where this passive active classification idea came from. And now we also have more that we could explore, for example, gender effects, because in both studies, the participants were also gender balanced. In terms of age group, I don't think we will be able to answer this question through our data set because all these participants were young undergrad students from our institution.
Okay, thank you so much. So I think this was the last talk. So now we have the panel discussion. So I would like to ask all the panelists and speakers to join us if you want to share the camera. So Mohammed, we can start by a question and then we can coordinate the conversations. What if you start first?
Sure. Well, maybe I can start by asking this question. I mean, I shared a little bit about our own experience, but I wonder how has it been for you that you're not allowed to do any human subject research and all of this. So during the pandemic, how did you cope with the lack of human subject research? And that's true in general haptic research and more so maybe in neurohaptics.
I can actually start maybe. So first of all, we were in a strange situation here because we were actually allowed to continue doing the human studies most of the time. We developed our protocols of keeping the safety of the students and the research subjects. They had to declare that they don't feel any symptoms. And of course, during lockdowns, everything was during lockdowns it was not possible, but between the lockdowns, we could be in the lab. But I kind of had, my message to the students was start focusing on data analysis. Like we always have plenty of data lying around, and it was really kind of an opportunity. So only those who were really insisted on being in the lab and running experiments, we did some studies, but most of the message was just do some data analysis.
Yeah. Any other thoughts on this?
I think it was a challenge for, in many aspects, and as Ilana mentioned, perhaps if the data was collected before, I think that was a great strategy. So any other thoughts from the speakers, or if you want to share your experience about it?
Well, I think telemedicine, became a huge, this whole idea of using technology to acquire data remotely has become very important during the pandemic. So using haptic devices, using anything that could enable remote data collection, and just setting up the infrastructure for that became extremely prescient.
Maybe one thought about it, because I know that in the neuroscience community and the sensory motor control community, a lot of the labs have actually pushed toward the collection of data of subjects at home. So like using these Amazon Turk or stuff and developing these motor tasks that can be happening online. And this was kind of really nice because we start seeing studies with huge sample sizes, like hundreds of participants, because if you're employing this platform, you might as well collect hundreds of participants. And it made me thinking with respect to haptics, like there was a push of developing devices that would be cheap enough and deployable at homes of users, like the haptic paddle and all these efforts of using haptics in education where you can send those kits. So maybe now it's the right time to push those efforts even more forward such that we can do these massive experiments of people at home by just sending them kits home.
Yeah, actually, that reminds me of a personal experience with teaching a class about touch. And what I did, I actually created this wristband, like a very simple wristband that I sent to all the students because we had students from across the globe. And then we experimented through their term project with protocols that people could develop for creating interpersonal communication using vibro-tactile stimulation. And the students came up with really great ideas because they were physically disconnected and they had no option but to try out and experiment with different ways of communicating using vibration feedback. And I would say that there are great ideas that came out of this.
Yeah, I think as Sliman mentioned, you're using video-based analysis using Deep Lab Cut, right? You want to elaborate on that? We're using that as well. It's particularly helpful for certain kinds of movements, but not other kinds. So I just wondered about your experience. How do you get the complex hand movements from Deep Lab Cut?
Not easily. So we worked with the Vicon system, which is like $150,000 system. And then you have to use these, track these IR markers, and it's just a pain in the neck. Yeah. So we took Deep Lab Cut. I mean, Deep Lab Cut really is only built for 2 cameras. I mean, it in principle has the ability to use more than 2, but it's not really functional as, on the GitHub. So we spent some time, and by we, I mean, not me, but my postdocs spent some time, extending it so you can use 8 cameras. And then, and now that you have more than 2 views to figure out, to triangulate the position, now there's all kinds of new difficulties that arise about how to actually triangulate the position of each marker. So by the way, all that stuff is online. So I encourage you to take a look at it if you so that you don't duplicate effort. But there's still the issue that there's a lot of occlusion that goes on. And we also tattoo the hand just so to kind of break some ambiguities if they arise, because the fingers are kind of look the same. But there is still a lot to be done in that, there's always occasionally a marker drops off for a period, and then, you have to have your squadron of undergraduates kind of marking that. So I'll just tell you a couple of things. One is we're building a database of hand movements. And of course, these are deep learning networks. So the more data you have, the better they're going to be at it. 2, we're building software to, take an arbitrary number of cameras and then, intelligently bringing you to views, intelligently as in like, what is the camera that's most likely going to be most informative about this marker? And then sort of, doing it every few frames, so you don't have to label every single frame, and then interpolating and all that stuff to kind of make the sort of cleaning the labeling step faster and streamlined. So all that stuff will be available down the road, but it's definitely a work in progress.
Great. And it sounds like that's not something you can do remotely, right? You need 8 cameras. So
Yeah, no, right. You need 8. Yeah, exactly. No, it's not. I mean, I'm not chiming in on this remote thing because I do have a human component to what I do, but most of what I do was with non-human primates, and actually we never stopped doing it. I mean, just because when you have you punch a hole in the skull, you can't just stop doing experiments. And everyone is in their own room, so it was pretty safe. It was as safe as any place. So.
Yeah, our experience was also interesting. We were shut down from March 2020 till just about early September 2020, and then we were allowed to resume human subject experiments in person. We just had to restrict our population to be Rice community because of the testing and contact tracing that they were doing on campus. So we had some work in sort of planning experiments. I did have students running pilot experiments on family members, students who had gone remote, so that when we had some advance notice that it was likely going to be able to resume. So So we were also able to continue collecting data once we hit September and have done it consistently since then.
Yeah. Any other thoughts? Or maybe I can move on to the second question, which is a question that I always get from PhD candidates who would like to get into neurohaptics. And they always ask this question because they're intimidated by the multidisciplinarity of this research. Like they need to learn about neuroscience, haptics, psychophysics, maybe, and other things. And of course, still the engineering background of creating haptic interfaces and things like that. So what would be your advice to, let's say, a fresh PhD student looking for a research topic in neurohaptics? What would your advice be for those students? What kind of background they need to pick up and what kind of interesting research that they could get into? And I see Etienne has raised his hand, so please go ahead.
Okay, so I think it's a nice question. So I have another question. So to Marcia. So I have been to the Haptics conference, the World Haptics and Haptics Symposium for a while, but it used to be very nicely interdisciplinary and a lot of discussion and fights between different misunderstanding and so on. And so I think if I could, I would advise, actually I try with my starting student to put them in, I would say, put them in that conference and let them see what fields they prefer and the different approaches and yeah, basically they may be able to get advice by themselves better than by me, in a way, from the other people. So Marcia, is that still a lot of discussion and so on? Can you please tell us?
Your question, so for the haptics conferences, is there a lot of discussion?
Yeah.
Yeah, so I think it varies. There's certainly much more discussion and healthy debate, I think, in the workshops and cross-cutting challenges than there has tended to be as of late in the traditional paper presentations. Although I don't think this is unique to the haptics community. I think in general, at least the conferences that I attend have gotten tamer in terms of the discussion and Q&A. I long for the days when there would be, pointed questions and putting people on the spot. But I would say it is still a highly interdisciplinary community, and that's the benefit, right? So, I mean, you can see it on this call, on this webinar itself, but that's sort of reflected through the whole conference. So I do think you get the perspective of, those who are coming at haptics from a neuroscience perspective, those coming from a rendering, a device perspective, a controls perspective, a psychophysics perspective. You do sort of see the intersection of all of that. And I think it's a great venue to come and sort of get exposed to the field. And then if you decide that you are really, so Sleeman, I know this isn't your primary community, right? You're much more on the SFN side of things. So then you sort of can figure out where your passion is, and maybe haptics this community becomes part of your community of research engagement, but then you may have something much more focused on your specialty, be it the neuroscience aspects or neural recordings, or I'm more on the dynamic systems and controls side. So I might have a different community that I interact with.
Mm-hmm. Yeah, so it's still pretty much multidisciplinary. So for myself, if I can compare, for example, to robotics conference, of course, it's much more multidisciplinary, and of course, I like it. For me, it would be, so the perfect world would be something like that with not only haptics, but also vision and other sensory modalities. Mm-hmm. But it's close to the ideal.
Yeah. So maybe I can actually ask we can ask a different type of question now. And I think one of the topic that we discussed today.
Can I actually interrupt real quick? before you move on to a different question? I'm sorry, but I think
sure. Don't worry about it. Go for it. Yeah.
And what I'm going to say is going to sound very much, it's not going to be very surprising given that I'm, a neuroscientist at heart, but, and I don't do haptics, so I could be completely wrong about this, but, I do neuroprosthetics, brain machine interfaces, sensory restoration and stuff. And I think actually there's a lot of the same stuff there. And what I tell students in those realms is if you want to do a brain machine interface, or like you're interested in creating sensitized bionic hands or whatever, study the sensory system. You know what I mean? Like, there's a lot, especially in BMIs, and I don't, maybe in haptics too, there's a lot of people who are just have this very strong engineering background, and that's great, and that's obviously necessary, but you're interacting with a sensory system and there's a lot known about it. I mean, there's a lot also not known about it, but it seems like bringing some basic knowledge about the sensory system that you're interfacing with seems absolutely critical. And I feel like oftentimes missing, so for instance, there's like, oftentimes you have this effect, you're like, look we got this effect and we don't understand it. It's this magical effect, but like you just tell me the effect. I mean, this is a cartoon example, right? But it's like, well, if you knew that, for instance, there's multiple sensory, receptor systems and that have different vibrotactile frequency sensitivities, that could actually explain your effect, something like that. And it's usually not that, most people do know that much, but there's a lot of this stuff about the neural system itself, about the skin mechanics. There's a lot of the stuff on the skin mechanics themselves that are critical in understanding, the resulting sensory experience. And I feel like you're not going to do good work unless you have at least some pretty good understanding of the sensory system, is what I would tell them.
Yeah, and I'll just piggyback on that too. I think it's a pretty fair conclusion to draw that this group does not do their research in isolation either. We are all collaborative in what we do. And so, that's not to say that you can just say, well, I do this part, right? And I'm going to go to somebody else for the brain machine interface, or I'm going to go to somebody else for the hardware design. You have to have the vocabulary enough to be able to communicate and collaborate. So you need a broad knowledge, and I think that can be what's intimidating, but you can also be a specialist within that broad field. So, I know about the different frequency response ranges of mechanoreceptors in the skin, thankfully. But when I really don't understand anything, I'm going to go across the street and talk to Jeff Yao. I'm going to say, Jeff, help me out. Like, I need to understand this better, right? So that was a little, so excited about that collaboration. But I couldn't have those conversations with him in a meaningful way if I didn't also have a shared vocabulary with him. So I think there's a balance between sort of becoming familiar and reading the literature and knowing the field, but then also having enough of your own specialty domain knowledge that you bring something unique to a collaboration that you can only do with somebody else together.
Totally agree. I mean, I didn't want to overstate it that you need to become a neuroscientist or you suck, but at least be aware that there are questions that somebody else might be able to answer.
I would also maybe add just a little comment for the intimidated student, because obviously if you're trying to become this multidisciplinary researcher and you might try to communicate with like several communities, you might have the experience that I often have myself and sometimes my students have of feeling inconfident in any community that you are part of, because, I'm not a robotics researcher because I was never trained as a robotics researcher, and I'm not a neuroscientist because a lot of the time I work with the devices, and maybe I'm not, reading enough of the neuroscience literature because there are only that many hours a day. And then that's something to be ready to deal with, this sort of, I don't know if you call it imposter syndrome or insecurity or whatever, but just trying to understand that if you're choosing the path of being multidisciplinary and trying to be in these many communities, you will kind of pay the price of feeling there are people in each community who know much more than you do in their own field. And if you're comfortable with that, it's fine. And if not, you may want to become more specialized in one of the fields.
This is a very interesting comment. Actually, I mean, connected to the point I wanted to mention that was actually related to the same topic that we're talking here. That was about the education in the field. So I think, like, for example, now, because many of the people in this talk, they're also connected to robotic community. In robotic community now, currently, there's a lot of very systematically designed courses and educational material for students. For example, at NYU, we have like 4 or 5 courses on robotics. So if someone take all 4 courses, then that person will feel, okay, I know robotics, I can do research in robotics. But when it comes to, I don't know, neurohaptics, which is the intersection of neuroscience and haptics, I often find that in many universities, there's a kind of a possibility, maybe in most of all universities, there's this lack of a very systematically designed syllabus for kind of education of those students. So I'm just thinking maybe if there should be a move, or if there should be a collective initiative from the society to put together an educational material for students who want to start doing neurohaptics, which is the intersection of neuroscience and haptics, and to prepare them to do research instead of letting them to go and explore many different overlapping fields, and as Ilana mentioned, sometimes there are other feelings that they may have. So I don't know how would be how you would comment on that possibility of collective initiative for educational material in this field.
I mean, again, I'm not a haptics person. I'm not a card-carrying haptics person, but I've been to your meetings and I embrace your efforts. It seems to me, though, that I'm not sure that haptics is that sort of, cohesive a field that you could say, okay, here's a textbook, here's the textbook. I mean, there's a lot of different subfields. It depends on what kind of questions you're interested in, what kind of subdomain you're working within. And again, there's some again, I'm just going to repeat myself because I'm just like, you wound me up, I'm going to say it. Like, one thing we all have in common is the sensory system, right? But beyond that, I think my impression is that it's very kind of diverse beyond that.
I think there's some good foundational haptics courses if you come from an engineering or maybe even a CS or HCI perspective, but they tend to cover sort of the basics of sensory perception and then move on to, okay, devices and sensors and rendering. And so I think it's unlike, a series of robotics courses where, I could name off the areas at ICRA, and if you had a class in each of those, then you're sort of, they're similar enough that you could have the background across all of them. I think, like Suman says, it's a really broad area. So you have to sort of decide if you want to be on this sort of, neuromechanics piece, then there's a whole nother circle in the Venn diagram that you need to get into.
Yeah, I agree with Sliman. I also don't think that there is really, so to me, is that what I was telling before, there is no haptics. Not only haptics, and yeah, so sensor is a big part, and integrating with some robotics and some physiology and so on. So we have a master's where we try to do that. Of course, a master's is very short, especially in the UK. It's only 1 year, so you cannot take it too seriously, I would say. But still, so you get a student getting courses in physiology, robotics, machine learning, ear mechanics, brain-machine interface, things like that. And I guess this student will start to have a background and be able, we hope, be able to make some synthesis of these different aspects. And so one thing that is sure is that this master's is very attractive. I mean, we have so many applicants every year. We cannot take many because you have the limit of the project you can supervise finally. But so I think if we offer such curriculum, there is quite a few students who are interested in that. Because of the wave of machine learning, of course, but not only.
Yeah, I agree. I mean, so here in NYU, I designed a course on haptics and telerobotics in medicine for undergraduate students, and the students liked it very much. I mean, I got a lot of positive feedback. But what I also hear that they couldn't find like now if you want to do machine learning or robotics, there's a lot of online courses that they can take to, like, I don't know, to cover different aspects. But my point is more, if there would be any systematic design of a series of curriculum, it's great. And I'm familiar with the program Etienne at Imperial, and I agree, that's a great program. So I think programs like that can be really beneficial for students who want to get into different angles or aspects of it. But I'm sure in future there'll be more. So yeah, that's an interesting, I think, topic from my point of view.
Yeah, I don't know if there will be room for one more question, or we can, I think we have about 6 minutes before we close the workshop. But maybe I just take advantage of these last 6 minutes and just ask the last question, I promise. And that would be, if there is one simple research question that you want between now and the next time we meet, you want it to be answered, what that question would be.
Okay, so I'm speaking too much. So there are many questions. I'm sure all of us have some. But one thing that is in haptics actually is that it is still fragmented into tactile and proprioception. Also, they have to work together if you want to get an understanding of the world and be able to do something, some manipulation. So maybe it could be a good idea to try to put people from these two so far mostly separate parts and trying to find common ground.
Mm-hmm.
Amen to that, given the fact that I was just talking about those two aspects.
Yes, in fact, you told that. I agree. Yeah.
I mean, one of those
neuroscience
questions.
If we have to vote, I joined this one as well. But also maybe to add another one that I mean, of course, there are many questions that are interesting, but for one that I've been struggling in my mind and I don't have good ideas how to address is the question. It's kind of a similar question to the coordinate frames that people have been looked at for visual system compared to the forces, the joint space and everything. Now, if you want to extend this to add the tactile system into the story, not only the kinesthetic, then it gets a bit even more complicated, and maybe trying to tease those reference frames apart would be interesting to me.
I just want to say I totally agree, and I what that question, there's like, you look at an object and you can grasp it, and you're pre-shaping your hand to that object really precisely, right? Which means that you have this visual representation of the object, and somehow it's transformed into some kind of motor representation, and that motor representation has to interact with sensory, somatosensory representations that are both tactile and proprioceptive. So to me, those are kind of related questions. Like, first, before you understand these reference, how you transform the reference frame, you need to understand what is the haptic reference frame, right? And that is one of the big, I didn't have time to talk about this, but that is one of the questions we're trying to understand, is how is it that the brain is going to encode the hand? It has, the arm is easy because basically all the arm does is put the hand somewhere in three-dimensional space. So it's 3 numbers, right? But the hand is a shape, right? It's a specific shape. How do you parametrize that shape somehow in a way that's useful is a super interesting question.
Wow.
And I just want to, my question here is for pre-T. I mean, I'm not expecting you to answer this question, but one of the frustrating questions that's related to your work, and your just field in general, is that we know that somatosensory cortex is important for motor behavior, right? As evidenced by the fact that if you have a stroke in somatosensory cortex, that's going to cause major deficits, especially deficits in manual behavior. What is frustrating to me, though, is what the hell does the somatosensory cortex do in the context of guiding motor behavior, right? I feel like it's one of the most, and I'm like it's one of my failures, if as much as anybody else's, right? Is what is the role of somatosensory cortex in guiding online behavior? I think is a question that really is not very well answered, because of course you have all these subcortical loops that are also kind of contributing to that, right? So, what do you think? Do you think that's an interesting question, Preeti? No?
Oh yeah, absolutely. It's key, just like the change in the reference frames. Sorry, my internet seems to be a little unstable. Can you hear me all right? Thumbs up?
Yes, we can hear you.
Yes, we do hear you. Yes.
Can you hear me all right?
Yes, we do hear you.
Oh, okay. Yeah. No, I think that's a key question. Exactly how does the motor behavior evolve based on all of the sensory information that you are getting? It's the visual, then there's proprioceptive, and eventually you touch the object. There's so many transformations occurring along the way. And to understand that is quite a bit. It's quite a feat. We know bits and pieces, but to put it all together is a whole other deal. And I think that from a patient's perspective, we actually, it's like being a blind pilot, but we don't even have all the tools to land the plane. They're just holes in our understanding. So there's a lot of work to do before it could be used intelligently to inform recovery.
Great. So I think, Mohammed, we are at 2 p.m. and that means that I think we should conclude the workshop. I would like to thank you. Thanks a lot for all the invited speakers. It was an impressive event, and I personally enjoyed it a lot, and I learned a lot. So thank you so much for sharing all these amazing results and outcomes of your research. And I'm sure the students in the talks and many attendees, they also enjoyed that. We hit the number at the max. We were about 100 attendees at this event. So thank you so much for making this happen and accepting our invitation and presenting the amazing results of your work. So that's my 2 cents. Thank you so much.
Yeah. Well, from my side, I didn't want this to end. This discussion was very interesting, but I think we'll have to keep it here and until we meet next time, hopefully in person. I wish you all the best. Very special thanks to all our speakers, to WorldHaptics for helping us to organize this event, and of course for our fabulous audience with their questions and interactions throughout the talks and the sessions. So with that, I wish everybody a very, very pleasant rest of the day, night, morning, wherever you are. And until we meet, hopefully in person, as I said, stay healthy and well. Thank you very much, everyone, and take care.
Thank you all.
Thank you.
Bye-bye.
Bye.
So to which Western are we going?
Right.
To which what?
Bar.
Yeah, we can plan it.
Surely we should. We should.
Yeah, thank you for organizing again. Bye.
Thank you.
Thank you.
Thank you very much,
Bye-bye.
everyone. Take care.
Thank
Bye-bye.
you. Bye-bye.
Bye. Thank you. Bye.